Hi students, hope you are all doing good. Once you are done with the portions of mechanics, these 4 chapters you must revise for sure to ensure the maximum score from grade 11 topics. They are heat and heat transfer, thermodynamics, oscillations and waves. Yes, that is the list of the chapters for this recap video. So, shall we start? Yes, here we go. So, the beginning portion, out of the conventional the way we proceed, I have got separate list for the chapters. So we will be dealing with this particular property, that is thermometry and calorimetry first. Thermometry means the portion that deals with the measurement of temperature, and calorimetry is that portion that deals with heat and heat transfer. Okay, so separately we are dealing because definitely that will make solving the questions related to temperature measurement and heat transfer bit more easier for you guys, and the basics that we are studying here, that will help us in the portions ahead, that is thermodynamics for sure. Okay, little portions from KTG we will be taking it over here, especially dealing with the work done in different thermodynamic process and all. So we will be getting back to that portions like little bit, so that you can understand the portions here this time better. Okay, so as I told, thermometry and calorimetry, that is the list of that is in the list in the beginning. So here, first of all, we are going to deal with simply the definition of thermometry. Okay, and of course, what is thermometry? The branch of physics that deals with the measurement of temperature, and the measuring device that is going to help us in this is known as thermometer. Okay, moving to the next, we have heat. Okay, see here, this was thermometry and calorimetry. Here we deal with what is thermometry, and here comes what? Heat. Heat is the form of energy that will be transferred from one body to another if there is a temperature difference between that two bodies. Okay, it's that heat energy which is transferred from one body to the another one if there is a temperature difference. Okay, so temperature difference is the mandatory condition for heat energy to transfer. All right, now what is the SI unit for heat energy? Definitely it is what? Joule. Okay, and what is actually responsible for that heat energy? So I said to the heat energy, the transfer of heat energy to happen, temperature difference is mandatory. Okay, now the point is, what is actually responsible for that capacity to do work or energy? What is the reason for that heat energy? It is translational, vibrational and rotational motion of the constituent particles present in the system. Are you getting me? So the translational, vibrational and rotational energy of the constituent particle present in the system is responsible for the heat energy. Okay, so once the temperature difference is there, so between two system, if the temperature difference is there, so definitely the one which is having higher temperature will be having more amount of energy associated to the constituent particles, and the one which is having lower temperature, it will be having lower value of energy associated to the constituent particles, so it will flow from the higher energy level to the lower energy level. That is what actually happens, and that is why the temperature difference is mandatory. And last I told you about the unit, and SI unit is definitely joule, but the practical unit is not that, and the practical unit is what? Calorie. And what is the relation between calorie and joule? 1 calorie is equal to 4.18 joule. And how we define actually 1 calorie? 1 calorie is that particular heat which is required to raise the temperature of 1 gram of water through 1 degree Celsius, and precisely speaking, that temperature difference is from 14.5 degrees Celsius to 15.5 degree Celsius. Okay, now let's go to another portion, that is the mechanical energy or work and its equivalent of heat. Okay, that means if we have got x joule of energy, and what is the equivalent heat of that much amount of energy, that is a point. The relation is W is equal to J times Q, where J is known as joules mechanical equivalent, and remember, J is not at all a physical quantity, it is just a conversion factor. It is just a conversion factor, and we already discussed what is that conversion factor. It is 4.186. So W is equal to JQ. I repeat, W is equal to JQ. That is the relation between work and the equivalent heat of the work. Is that fine? Now let's move to the next, that is temperature and measurement. Okay, so what is temperature? Basically, the temperature is the measure of degree of hotness or coldness. I repeat, it's degree of measure of hotness or coldness. Okay, fine. And on the laboratory, as of now, the maximum value of recorded temperature is 10 to power 10 Kelvin, and the minimum is 10 to power minus of 8 Kelvin. And the next thing what I am going to tell you is important, especially regarding the the questions related to kinetic theory of gases. That is, you will be coming across these two things, NTP or STP. And definitely you must know what is the values. There the temperature is going to be what? 273.15 Kelvin or 0 degrees Celsius, which is also marked as 32 degree Fahrenheit. Okay, and next is different scale of temperature. Before starting this topic, I would like to tell you why should we go through this. We must go through this particular portion just because there are cases where the temperature is going to be provided you in one scale, and they will be expecting you to convert that into some other scale. Alright, so doing so, you must know what is the relation between these two temperature scale. Okay, and there the basic thing that we must know about all this scale is 3 points. Point number 1, what is the melting point of ice? I repeat, what is the melting point of ice for a given scale? Second thing is, what is the boiling point of ice as per the given scale? And third point is, how many number of divisions are there between the maximum value as well as minimum value in the given scale? And what was the maximum value? Maximum value was boiling point, and the minimum value was what? Minimum value was the melting point. Okay, let's take one example that is the very first in the list, that is Celsius scale. As per Celsius scale, okay, we are marking the temperature at which the ice melt as 0 degrees Celsius and the boiling point of water as 100 degrees Celsius. Okay, see, I told you 3 points are mandatory. What were they? Melting point of ice, boiling point of water, and number of divisions. So here comes the third. There are 100 equal divisions. Okay, fine. Are you okay with that? Yes. Now come to the next, Fahrenheit scale. Here the ice melt at 32 degree Fahrenheit, and the temperature at which it boils, it's marked as 212 degree Fahrenheit, and number of divisions is 180. 0, 0, 100, 100 for Celsius, 32, 212, 180. Next is Kelvin scale. Okay, there melting point of ice is 273 Kelvin and boiling point is 373 Kelvin, number of divisions 100. Okay, next is Reaumur scale. There the melting point of ice is marked as 0 degree Reaumur, and here it is 80 degree Reaumur, and number of divisions is 80. Okay, now comes the most important relation. I will tell you how this relation is. Okay, now C is any temperature value in Celsius scale. I repeat, any temperature value in Celsius scale. Now here this is Z minus 0, and what was that 0? 0 was melting point of ice. So C minus 0 upon 100 you can see. Are you getting me? Now F is the equivalent value of C degrees Celsius in Fahrenheit scale. Okay, so here it was C minus 0 because 0 was melting point of ice. Okay, and in Fahrenheit, what was melting point of ice? It was 32 degree Fahrenheit. So here it is going to be F minus 32 divided by number of divisions, 180. Okay, that is equal to same temperature value in Kelvin scale, that is K, minus what was the temperature of melting point of ice as per Kelvin scale. It was 273. So here it is going to be K minus 273 divided by 100, because number of divisions is 100 only. That is equal to the temperature in Reaumur scale, that is again taken as capital R only, and there the melting point was what? 0 degree Reaumur. So R upon again number of divisions is what? 8. I hope you got it right. Okay, so making it bit more easier to understand, I would like to mark it as this: T degrees Celsius minus 0 upon 100, that is T Kelvin minus of 273 upon 373 minus of 273. So here this is 0, okay, here this is the number of divisions, and in Fahrenheit it is T degree Fahrenheit minus of 32 divided by 212 minus of 32, number of divisions, that is equal to T degree Reaumur minus of 0 all divided by, it was 80 minus of 0. This is how we can connect, and the simplified version of this one is what you have over here. Okay, so temperature in Celsius scale minus melting point of ice divided by boiling point of water minus melting point of ice equal to same temperature in Kelvin scale minus melting point of ice divided by boiling point of water minus melting point of ice equal T degree, the same temperature in Fahrenheit scale minus 32, that is melting point of ice divided by number of divisions, that is 212 minus 32 equals same temperature in Reaumur scale minus of 0, that was melting point of ice divided by 80 minus of 0. I hope you got it right. So this is the mandatory relation that you must know regarding temperature conversions between any scales. Was that okay? Shall we proceed? Yes. Here comes the next, that is absolute temperature. Okay, this is the lowest temperature possible for a given body. Okay, and that is, we call it as absolute temperature. Okay, and that is nothing, it is the minimum temperature nobody can have a lower than that, and that is 0 Kelvin. Okay, and the next one is thermometric property. I repeat, thermometric property. Okay, now you might be wondering, why is that important to deal with thermometric property in this chapter? I will tell you why. Because it is that thermometric property which enable us to measure the temperature variations. Okay, by studying thermometric property only we can measure the temperature, and by this time you might be able to conclude what is thermometric property. Any property associated to material that changes and that changes can be related to the temperature. Okay, that is known as what? Thermometric property. So the property that changes with respect to the change in temperature is known as thermometric property. Okay, and out of that, the first one is pressure of gas at constant volume. That is very important. If we measure the temperature of pressure of a gas at constant volume, then the variation in pressure, it is a linear variation and quite easy to measure. And how they are connected is P1 by T1. That means if P1 is the pressure of any given gas at constant volume at T1 temperature, then P1 by T1 is going to be P2 upon T2, where P2 is the pressure of the gas at a new value of temperature, that is T2. Most important part that you must not miss here is all this relation we take as based on ideal gas relation only. Okay, and second thing is here the volume is kept at constant. Now you can have another relation here, that is Pt equal to P0 into 1 plus T divided by 273. Pt equal to P0 into 1 plus T divided by 273. Again, an important point over here, the temperature mentioned here, that is smaller to T is the temperature, and that need to be in Celsius scale. Alright, so rearranging this, you will get this particular relation as well. And using constant volume gas thermometer, the maximum value of temperature that you can measure is 500 degrees Celsius and the minimum value that you can measure is 200 degrees Celsius, minus of 200 degrees Celsius. I said it as 200, it is minus of 200 degrees Celsius. Okay, now let's go to the next, that is electrical resistance of metals. Okay, so we are dealing with the thermometric property, how different properties of material can be changed with respect to variation in temperature. So the first variation we studied about the variation in pressure of a gas if volume is kept constant, and now it comes the resistance. So how the resistance changes is RT is equal to R0 into 1 plus alpha times T plus beta into T square, where alpha and beta are positive constant. While studying, we came to the conclusion that beta is comparatively very small. So there we take only up to here because this is comparatively smaller. Okay, so the relation is RT is equal to R naught into 1 plus alpha times T, where R naught is the resistance of the material when the temperature is 0 degrees Celsius. Okay, fine. And alpha that is known as temperature coefficient of resistance. So this is another thermometric property, that means the one which changes with respect to the temperature. And so of course, once you know this relation RT is equal to R0 into 1 plus alpha times T, there we can have separate relation for alpha. And once you know the different value of resistance, for example, what is the resistance of the material when temperature is equal to 0, what is the resistance of the material when temperature is equal to 100 degrees Celsius, and if we know one more value, that is when T is the temperature, RT is the resistance that we measured. So then measuring the all given values, like knowing the value of R0, R100 and RT, of course along with the value of alpha, we can easily calculate what? The temperature. Okay, and again another important part is the minimum temperature that we can measure by identifying the resistance of a given specimen, that is minus 200 degrees Celsius, and the maximum is 1200 degrees Celsius. Minus 200 degrees Celsius and 1200 degrees Celsius. And the next one is the length of the mercury column. That means if we have a capillary tube and mercury is filled, then the height of the mercury column, that will be linearly varying. And how that linear variation is happening, it is almost similar to that of variation in resistance. L suffix T, that is equal to L0 into 1 plus alpha times T. And here please don't confuse with alpha here. There alpha was temperature coefficient of what? Resistance. Here alpha is not that, that is coefficient of linear expansion. Okay, and next is thermometers. I already told you what is thermometer, the device that help us to measure the change in temperature and hence the temperature. Okay, that is what we call it as thermometer. And how the thermometer help us to measure the temperature or identify the variation in temperature is by analyzing the variation in thermometric properties. Okay, now let's see how that is analyzed is going to help us in measuring the temperature of a given specimen once we know certain parameters. Okay, like here. We know the length of the mercury column once the temperature is at 0 degrees Celsius, 100 degrees Celsius, and that condition if these two heights are marked, I repeat, the length of the mercury column at 0 degrees Celsius as well as 100 degrees Celsius is properly marked, and if the length of the mercury for a given temperature, height of the mercury for a given temperature is a measurable value, then we calculate the temperature as L sub t minus of L naught all divided by L of 100 minus of L naught into 100 degrees Celsius. Here L sub t is the height of the mercury for a mercury column for a given value of temperature. L0 is the height of the mercury column for 0 degrees Celsius. L100, that is height of the mercury column for 100 degrees Celsius, and L0 I already told you, again I repeat, that is the height of mercury column for 0 degrees Celsius. So if of course these four values are quite a measurable thing, that means the height of the mercury column. So just by taking the measurement of the height of the mercury column, here we easily calculate what is the temperature of the given specimen or sample. Okay, and that is what basically a thermometer does. Fine. So this is how a mercury thermometer helps us to measure the temperature. Here comes the next, that is constant volume gas thermometer. There, instead of measuring the temperature, we will be measuring the pressure. Okay, we will be measuring pressure. How to measure the pressure of a given sample, that we already studied in fluid. So here, in such a way, we measure the pressure at 0 degrees Celsius, pressure at 100 degrees Celsius, and pressure at given temperature T. Then Pt minus P0 upon P of 100 minus P0 into 100 will be temperature in Celsius scale. Next comes resistance. Okay, RT minus R0 upon R of 100 minus R0 into 100, that is going to be what? That is going to be the temperature in Celsius scale again. Alright, and the next one is thermal expansion. So the expansion happens to any material once heat energy is transferred, is known as what? Thermal expansion. That means if we transfer heat energy to any particular given system, definitely the temperature will rise. Okay, if the arrangements are made so because of that, the expansion will happen to the dimensions of that given sample. Fine, then that type of expansion is known as what? Thermal expansion. So while basically the thermal expansions take place, okay, the change of state of the given system is changing. All right, so we'll be dealing that in detail. Like what all are that thermal, what all are the state, like how we define the state of the given system is changing. So if the state of the system is being changed, then what exactly mean by the change in the state? Okay, we will be just dealing with that in later on. So basically what is thermal expansion is the expansion happens to any particular body, can be solid, liquid or gas, whatsoever it may. Okay, if allowed, the expansion happens to the given system just because of the transfer of heat to it is known as what? Thermal expansion. And here we will be considering three types of expansion. The first one is the linear expansion. That means how the length is changing, and how the length is changing. It's going to change as L2 is equal to, that means the final length, L2, that is equal to L1 into 1 plus alpha times delta T, where delta T is the change in temperature and alpha, it is known as coefficient of linear expansion. Coefficient of linear expansion. Next is superficial expansion. Here, this is the change in area. Okay, and the area is changing as what? A2, that is equal to A1 into 1 plus beta times delta T, and here beta is nothing, the coefficient of superficial expansion. A1 and A2 are the initial and the final area, and the next one is cubical expansion. So here, instead of length and area, volume is changing. And how it's changing? The change can be marked as V2, that is equal to V1 into gamma times delta T, where gamma is the coefficient of cubical expansion. Okay, and how gamma is connected? Gamma is connected as delta V upon V into delta T, where delta V is the change in volume, V is initial volume, and delta T is the change in temperature. Okay, and now since we discussed about gamma, let's try to recollect what was alpha. Alpha was delta L upon L into delta T, and what was beta? Beta was delta A upon A into delta T. Now it is important to identify the relation between alpha, beta and gamma. So the relation between alpha, beta and gamma is alpha is to beta is to gamma is equal to 1 is to 2 is to 1 is to 2 is to 3. That is the relation. Alpha is to beta is to gamma is to 1 is to 2 is to 3. It's very easy to identify. Alpha is for one dimensional expansion, beta it's for two dimensional expansion, and gamma that was for three dimensional expansion. That is why it is 1 is to 2 is to 3. Now, while dealing with the expansion of the liquids, we need to deal with the apparent expansion as well as the real expansion. You might be wondering, how come this apparent expansion and real expansion, like what does it actually mean? I will tell you a real example. Let us consider a liquid which is kept inside a container like this, and anyhow if we provide some heat, and if this liquid changes its volume in this way, like it got expanded like this, now I can mark this as the change in volume, and just try to consider a situation like this. What if the container also was expanding like this? Then definitely you will be identifying a change in volume as this thing only. So what you observe is not exactly the change in volume. The actual change in volume is less than what we measure here, and what we measure here is now the apparent change in volume. Okay, now this V apparent, delta V apparent is now going to be delta V actual, okay, minus of delta V of the container. Delta V of the container. This relation is very, very, very important, and from there I can say that, so in such a condition, the gamma what we observe here, that is what was gamma? Gamma was delta V upon V into delta T. So what's the gamma what we are going to calculate just by measuring the final volume as well as initial volume is not going to be the real, it is going to be the apparent value. So in that case, gamma apparent is going to be delta V apparent okay upon actual volume V into delta T. Okay, and what about gamma real? Gamma is going to be a real change in volume into original volume, I mean divided by original volume into change in temperature. And once we deal with the real value of gamma, so real value of gamma, that is going to be gamma apparent, okay, gamma apparent plus the gamma value of the container. Actual value of gamma is going to be gamma apparent plus gamma of the container. So that is also a very, very important relation. Alright. Next one is anomalous expansion of water. That means something which is different from the normal variation. Normally what happens, it is once we increase the temperature, the volume should increase, and once we decrease the temperature, volume should decrease. In case of water, Once you continuously decrease the temperature from 0 to 4 degrees Celsius, it contract, and from 4 to 0 it expand. Okay, that is what we call it as what? Anomalous expansion of water. Next is thermal expansion of gases. Okay, so first we dealt with expansion of solids, and here we dealt with expansion of liquid, and the next one is expansion of gases. Now the gases, that can be the expansion. Once we consider the expansion of gases, we need to consider it under two certain conditions. The first one is by keeping the volume as constant, and second one is by keeping the pressure as constant. I repeat, by keeping the volume as constant as well as by keeping pressure as constant. And just because of that, here we are going to have two different coefficient of volume expansion, that is gamma suffix V, okay, and gamma suffix P. Alright, now at gamma suffix P, don't get confused, at gamma suffix P, volume is constant, and at gamma suffix V, pressure is constant. Okay, don't get confused. I told you here two type of variations we make by keeping the pressure as constant and by keeping the volume as constant. Okay, that means we are going to provide heat to the given sample of gas by keeping the pressure as constant as well as by keeping the volume as constant. Now how the pressure is going to change and how the volume is going to change, based on that we are going to get two different value of gamma. First one is gamma suffix V and second one is gamma suffix P. For gamma suffix V, its coefficient of volume expansion once pressure is kept constant, and here it is pressure coefficient once volume is kept constant. So the relation is exactly the same. While dealing with gamma value, we got it as delta V upon V into delta T, isn't it? So if it is gamma suffix V, which means the pressure is kept constant, that's going to be again the same thing, V2 minus V1 upon initial value, and T2 minus T1 is the temperature. Okay, and now, but just one thing you must understand, there we got it as delta V upon V, and V was marked as initial volume. Okay, and here it is V2 minus V1 upon V0. I repeat, V2 minus V1 upon V0 into T2 minus of T1. Similarly, gamma suffix P, it's going to be P2 minus P1. I repeat, P2 minus P1 upon P0 into T2 minus T1. It's not P2 minus P1 upon P1. It is P2 minus P1 upon P0, where P0 is pressure at 0 degrees Celsius and V0 was volume at 0 degree Celsius. Now, let's deal with the variation of density with respect to temperature. We already dealt with this topic in fluids. How the density is going to change is rho dash is equal to rho into 1 minus of gamma times delta T. This is how the volume is changing. This is the standard relation basically. Rho is equal to rho naught into 1 plus gamma times delta T all raised to minus 1, and while we take this as a small value, so of course we ignore the second order as well as a third order relation, and finally we will get it as gamma is equal to gamma into 1 minus of gamma times delta T, and gamma is the final density and gamma naught is the density at 0 degree Celsius. And next is practical application of thermal expansion. Okay, first one is like wherever we need an expansion immediately and a normal temperature that need to be fit and all, so we definitely consider for that one. So here once the rail are laid down, okay, then we basically leave some space in between, because once the the movements happens over the rail, okay, and because of the temperature variation and all, there is a chances of what? Expansion. And if that space is not provided, then the bending of the structure may happen, and later on that lead to fatal conditions. So just to balance that, that space is left over. And second one is, normally once transmission cables are laid, then we keep it not tightly fixed onto the poles, because again, because of that thermal expansion node, that dimension variations can be expected. Then the capping of the wheels, so many applications are there, and out of that just 4 to 5 are here in the list. You can go through that. Okay, and refer NCERT textbook also associated to this one for sure, because there can be questions associated to this one, especially in assertion reason type problems, as well as match the following areas. Theoretical concepts are basically generally asked from that particular area only. Now next we move to thermal equilibrium condition. Okay, so what do you mean by thermal equilibrium condition? When there is no heat transfer between two systems. I repeat, when there is no heat transfer between two systems, that particular condition is known as what? Thermal equilibrium condition. Next is about triple point of water. Okay, triple point of water. So what is triple point of water is basically at 273 Kelvin temperature and 0.46 centimeter pressure, sorry, 0.46 centimeter of mercury, like that, for that particular value of pressure, the liquid that is in equilibrium condition with it all the three states, that means gaseous, solid as well as liquid state. That means any variation in pressure or temperature can immediately change the entire thing into liquid or into gas, purely into gas, or into the liquid format. So that appears for particular given value of temperature and pressure only. So that point is known as what? Triple point of water. So the next topic is specific heat. So here basically specific heat, once we explain it for liquid or solid, and once we explain it for gas, the case is a bit different, and that we will be discussing on this particular slide, and that is very important once we deal with the topics in thermodynamics. Okay, so that need to be understood very clearly. So now in general specific heat is that particular amount of heat which is required to raise the temperature of 1 kilogram of substance through 1 degree Celsius. Okay, so the temperature change is 1 degree Celsius, and always you must keep it one thing in mind: the temperature change of 1 degree Celsius, it is same as that of temperature change of 1 Kelvin also. So that also must be there in your mind. So generally I told you what is specific heat. Basically it's heat required to change the temperature of 1 kilogram of substance through 1 degree Celsius. Okay, now I told you once we deal it with the case of gas, there we have to mention about specific heat at constant volume and specific heat at constant pressure. What is specific heat at constant volume and what is specific heat at constant pressure? The case is, I can explain to you something like this. Consider a case where we are provided with a particular sample of gas, and that particular gas is filled in a closed cylinder which is whose piston is basically locked. So piston is locked means piston cannot come down or piston cannot move up. That means the volume is fixed. In that condition, if we want to come up with a change in temperature of 1 degree Celsius, there the situation is different. Okay, and case 2, where we allow the piston to expand or compress in order to maintain the pressure inside the chamber, pressure inside the cylinder to be constant. In that case, if we want to come up with a temperature difference of 1 degree Celsius, there the situation is different. Okay, so case 1, volume is the fixed, or I can say the piston is locked. In second case, we create a situation such that the piston can adjust itself to maintain the pressure to be constant. And so in both this case, the amount of heat that we need to supply to come up with a temperature difference of 1 degree Celsius will be different, and that is why we explain it as C suffix V and C suffix P separately because situation is different. So the heat consumed by the sample for that particular mention 1 degree Celsius temperature difference will be different. I hope you got it right. Now on top of that, I would like to tell you about the unit as well as the dimensional formula. So of course the dimensional formula for specific heat is going to be L square T raised to minus of 2 theta raised to minus 1 or capital K raised to minus 1 you can say, and of course the unit is what? Joule per kilogram per Kelvin, because heat required for unit mass for unit rise in temperature, that is why it is per kg per Kelvin. All right. Now next is specific heat at constant pressure and specific heat at constant volume. I already told you what it is basically, and one more thing that you must know, the relation between C suffix P and C suffix V. Okay, and this is applicable for what? Gas. Okay, now C suffix P is specific heat at constant pressure and C suffix V is specific heat at constant volume. And always remember one thing, C suffix P, that is Cp, is going to be greater than what? Cv. And the difference between these two, that means Cp minus Cv, is going to be what? Capital R, where capital R is universal gas constant. Okay, so that is the relation between Cp and Cv in terms of what? In terms of capital R. Now there is one more relation, and that is Cp minus Cv is equal to what? Gamma. Okay, Cp minus Cv is equal to gamma. So this particular ratio, we can connect this to a degree of freedom. You might be remembering, okay, what was degree relation between gamma and degree of freedom? Gamma was equal to 1 plus 2 upon F. Okay, and what is gamma? Gamma is Cp divided by Cv. Okay, so that particular relation also need to be considered here. Fine. Now next thing is thermal heat capacity. Okay, what it is? Thermal heat capacity. See, while discussing about a specific heat, we had a discussion, C is equal to Q upon M into delta T. Okay, so here M is the mass of the substance. For example, we are having 5 kg sample of say water or iron, anything, any material whose mass is say 5 kg. Now in order to create a temperature difference of, I repeat, in order to create a temperature difference of 1 degree Celsius change from its current position, we supplied Q amount of heat. What? How much? Q amount of heat we supplied. Okay, to create a temperature difference of 1 degree Celsius for m kg mass of a sample. Now Q is the heat supply, total heat supplied, and M is the total mass we are having. Now for 1 kilogram of sample, what amount of heat will be required? Obviously Q divided by capital M mass will be considered. Okay, and see the temperature difference. Now you might be wondering, like, why, what is that 1 degree Celsius then? See, delta T is 1 degree only. Delta T is 1 degree Celsius. So delta T is 1 degree Celsius, and for 5 kg mass we supplied Q amount of heat, and so of course for 1 kg mass the heat supplied is going to be what? Q upon M, and delta T is 1, I told you. Okay, and if delta T is not 1, for example, from 10 degrees Celsius we raise the temperature to say 20 degrees Celsius. Now here delta T is going to be what? Delta T is going to be 10 degrees Celsius. Alright, now C is going to be capital Q upon 5 kg, isn't it, into 10. Fine. Now if it is 1 kg for the temperature difference, so here this is the heat required for what? 1 kg. And now the point is not that, the point is heat capacity. So specific heat capacity was defined for 1 kg mass. Okay, that was a standard mass. And now here heat capacity, that is not meant for a standard value, that can be for a given mass of substance. For example, we want to convert 10 kg of mass, okay, 10 kg of mass temperature from say 10 degrees Celsius to 20 degrees Celsius. Okay, now if somebody come up with say 20 kilogram of same sample and expecting the same temperature difference, now definitely the heat that we need to supply will be different. Okay, so the amount of heat which is required to create a temperature difference of 1 degree Celsius for a given sample, not for 1 kg, for a given sample is known as what? Heat capacity. Okay, so in that condition, if we go for the mathematical expression, while comparing the mathematical expression of capital H, that is his heat capacity, with that of specific heat capacity, this M term will not be there. M term is not going to be there. So I can write the mathematical expression for H as H is going to be Q upon what? Delta T. Now just have a comparison between these two. H is now going to be, I can say that from here, capital H is going to be what? M into C. So here is the relation between heat capacity and specific heat capacity. I hope you got it right. Okay, I repeat, the relation between capital H, that is heat capacity, and specific heat capacity, you can see it here. Okay, now moving to the next, that is water equivalent. Of course, one more thing is here, that is molar specific heat capacity. Molar specific heat capacity. Here, I can tell you what is that molar specific heat capacity. Before that, let me have a conclusion on heat capacity, specific heat capacity and molar heat capacity onto a single slide. So small letter c, that is specific heat capacity, is going to be capital Q, that is the amount of heat that we supplied, M is mass of the body, and delta T is the temperature difference that happened. So here this is the relation for specific heat capacity, and heat capacity is Q upon delta T. Next is molar specific heat capacity. Here this is small letter c and here this is capital C. This is going to be again capital Q divided by number of moles of gas present multiplied by delta T. That is molar specific heat capacity. Specific heat capacity and molar specific heat capacity, you can see the same relation here as well. Was that okay? Now let us move to the next, that is water equivalent. Okay, so here what we are expecting is, let me consider a substance like this. Okay, now we are providing delta Q amount of heat to this particular substance. Now the temperature of this body was T1 and that got changed to T2. So the temperature difference is T1 to T2, or I can say delta T, that is going to be T2 minus of T1. Alright, now I am having small letter m kg of water here. I am going to have m kg of water here. Now to m kg of water, we are providing the same amount of heat. And once the same amount of heat was supplied to m kg of mass, there also we observe a change in temperature from T1 to T2. So if this is the condition, then m kg of water is considered as the water equivalent of this given substance. Was that okay? Clear? Now let us move to the next topic, that is latent heat. Okay, now here we will be discussing about latent heat of fusion and latent heat of vaporization. Okay, and post that we will be discussing about a few conversions also. Alright, that slides are ahead. Now first of all, let us see what is latent heat. Okay, Now, please try to understand, once we provide, let this be some ice kept. Now, once we provide heat of say delta Q to this particular body, I mean this particular specimen which was ice, what happens is there are two possibilities of using this energy which is being received by the sample, that is ice here. Possibility one is it will use this heat to convert, to raise its temperature from lower value to higher value. Okay, and this higher value, it's not like till infinity it will happen. No, there's a particular limit. Okay, in case of ice, say for example, this is having a temperature as minus of 10 degrees Celsius. Now, once we supply delta Q amount of heat to this ice, so first of all, what it will do is delta Q amount of heat will be first used to convert it from ice at minus 10 degrees Celsius to ice at 0 degrees Celsius. Ice at minus 10 degrees Celsius to ice at 0 degrees Celsius. Now, once this ice reaches to, I mean the entire sample is now having a temperature of 0 degrees Celsius. Now, what happened? The remaining amount of heat out of delta Q1 part is used, delta Q1 part is used to what? To raise the temperature from minus of 10 degrees Celsius to 0 degrees Celsius. Now, out of the remaining, the second part, that means delta Q2. So, delta Q1 is the first part and delta Q is the second part. Now, delta Q2 temperature will be used for the phase change. So, once the, now what do you mean by phase change? Now, this is in solid state. So, it will be converting from solid state to liquid state. So, once this phase change is taking place, there won't be any change in temperature, only phase change is taking place. So, whenever phase change is taking place, keep one thing in mind, there won't be any change in temperature. Okay. Now, once there is a phase change taking place and let delta Q amount of heat, let delta Q amount of heat is given to this ice, okay, which was at solid state to convert to liquid state. Okay, now delta Q upon M, here there is no temperature change, that you must understand. So, delta Q upon delta M, this is known as what? Latent heat. What it is known as? Latent heat. This is the standard expression. Now, if it is from solid state to liquid state, then it is known as latent heat of fusion. So, it is Q upon M. Okay, that is from solid state to liquid state. Solid state to liquid state. And if it is from liquid state to vapor, then it is known as latent heat of vaporization. So, it's the relation is the same thing only. Just instead of L suffix F, we will be having L suffix V. So, here it is from liquid state to vapor. That is the difference. We got it? So, this is what this entire slide is telling about latent heat. Okay, it's all about the change in state. Fine. It could be from gaseous, solid state to liquid state, and it could be from liquid state to gaseous state also. And remember, here, once the transfer takes place from, the transition takes place from solid state to liquid state, the heat is being consumed by the solid. Okay, and if it is freezing, that means from liquid state to solid state, that much amount of heat need to be removed. Okay, so once you supply heat to ice, it got converted to water. Alright, now once you remove heat from water, what will happen? Water will convert to ice. Similarly, once you supply heat to water, it will convert from water to water vapor. And once you remove that amount of heat, then what will happen? The water vapor will convert to water at 0 degrees Celsius. Remember, there is no temperature change happens once there is a phase difference. That must be kept in mind. So, here Again, I would like to tell you C that is equal to Q upon M into delta T, capital H that is Q upon delta T, capital C that is Q upon mu into delta T, and L that is Q upon M. You must be very clear with these relations. Very clear. Was that okay? Fine. So that was all about the latent heat. Okay, few conversions are there. You can go through that. Okay, just take a pause and go through these conversions and all. Now, if I want to take you to the next one, that is Joule's law. Okay, so here this is few applications only. Fine. So theoretical portion, like if you can go through that, then if the questions that comes in assertion on reason and all, that will be bit helpful. It's all the practical case. Fine. So go through that NCRT examples which relate which they exactly tell about this conversion, phase change, immediate heat transfer, what all are the practical examples connected to that. If you go through that, that will be very helpful. All right. Now here few cases, and these are those cases which were directly, and means this case what we are discussing, if you go through the previous year questions, you can exactly come across this thing over there. So the first one is, of course, the topic what we are going to discuss is what? Joule's law. Okay, so what Joule's law says, basically whenever heat is converted into work, I repeat, whenever heat is converted into work or work is converted into heat. Okay, there is a relation. We already discussed this. What is W is equal to J into Q. W is equal to J into Q. Already we discussed about this in the previous segment. And so that particular Joule's law, if practically we consider a few cases, how we can identify the temperature change and all. Out of that, the first one is, let us consider a given amount of mass falls through a height of h. Okay, see, if a mass falls through a height of h, what is the expected change in potential energy? It is going to be mgh. Okay, so given mass is mgh. Now mgh is the work done by the gravitational force, and because of this work done, what amount of heat can be gained, what kind of heat could be released? That is the question. Okay, now of course work is being done by the gravitation, so it is getting some additional amount of energy because of the gravitational pull. So that additional amount of energy need to be converted into form of heat, and as a result of that, the temperature of that particular mkg of mass need to be raised. Okay, now definitely for that we need to identify if m into g into h is the additional amount of energy gained by this particular mass, then what is the equivalent amount of heat which is provided to that mass. So to find out that equivalent amount of heat, how we will find out the relation? Q is going to be W by J. So mgh is the work done. Mgh by J, mgh divided by J, that is going to be what? Q amount of heat. Okay, and now we all know that Q upon M into delta T, that is what? Specific heat. Okay, now what was Q? What was Q? Please tell me what was Q? It was mgh upon J. M into gh upon J, that was Q. Now M into delta T is going to be C. Okay, now what's going to be the change in temperature here? Delta T is going to be, of course, M and M will cancel each other, G into H all divided by C into J. That is going to be the change in temperature here, and you can see the same relation here. Okay, now another case. when m kg of ice block falls from a height of h, it parts m melt down is. Here, there it was water. So there we were expecting what? There we were expecting a change in temperature. Now here, what we are expecting? We expect m kg of ice to get melt, isn't it? So here in this case, if this was telling about the temperature variation, okay, now we need Q upon m. That's going to be latent heat of what? Fusion. Alright, again, what's going to be Q? Q is going to be, from here, Q is going to be what? M into, alright, G upon capital J. Alright, M into G upon capital J, all divided by M. That's going to be what? Latent heat of fusion. Now, this one and this one will cancel each other. Okay, now in this condition, L suffix F is going to be what? GH upon J. So here this is latent heat of fusion. Now, if latent heat of fusion is known, so this is what we find out, what latent heat of fusion, isn't it? Now, if latent heat of fusion is known, then we can definitely identify what amount of mass is required. So now let us consider this value is given. This value is given. Okay. Now in this case, so that means here you must understand mkg mass completely converted to what? Ice. Okay. Now here, if I want to calculate what is the height through which, so what is the height from which this need to be dropped so that the entire ice at 0 degrees Celsius convert to water at 0 degrees Celsius. So that H is now going to be latent heat of fusion into J upon what? Small letter g. Okay, so this is the height from which need to be dropped. And if L is given, so now definitely it's very easy to calculate what? The value of M. Okay, how we will be calculating value of M? So Q is there. What is Q? Q is M into G into H upon J. Isn't it? Now, we all know that Q upon M, that's equal to what? Latent heat of fusion. Isn't it? Now, just rearranging this, I can say that Q upon L suffix F, that's going to be what? M. Okay, fine. Now, from here, if I go for this particular relation finally, what is Q? M into G into H all divided by J, okay, into L suffix F, that's going to be what? M. Now here you must understand one thing, here this is M dash, that means that amount of mass getting converted. So I will be going for M dash here and M dash will be appearing here, and here this is the total mass. Okay, here this is total mass and M dash is that particular amount of mass of ice which got converted from a form of ice to form of water. Alright, I hope it was clear. Now, of course, about melting and evaporation and fusion and all, I already told you. Okay, in detail discussion, even this height calculation and all, what I planned, more than that we have already discussed. Okay, so of course here boiling is there, fine, and after that sublimation as well as Horforce. What do you mean by sublimation? Please tell me. Directly from solid to vapor, if the conversion take place, that we call it as what? Sublimation, and the reverse of this, that's known as what? Horforce. Alright, and calorimetry, what is calorimetry? That we already discussed. Okay, that particular branch that deals with the transfer of heat and the measurement, the particular branch is known as what? Calorimetry. And here, of course, what is the study now? The basic principle behind that study of calorimetry. Okay, basically the entire study of calorimetry is based on law of conservation of energy, and specifically speaking, law of conservation of heat energy. That means the heat energy which is being lost by any particular body is being absorbed by the another one. Okay, so basically, in short, heat lost is equal to what? Heat gain. Okay, now you might be wondering, like, what is the purpose of this particular concept and why we are studying about this? So this will basically help us whenever, if a hot body comes in contact, it could be physical or non-physical contact. So after what happens, the heat exchange between these two systems, cease, or you can say conversion take place. And what amount of conversion has taken place and all. This entire thing completely depends on what amount of heat is being provided and what amount of heat is being absorbed. So if it is an isolated system where one hot body and cold body is coming in contact, so there is no other source of heat. The amount of energy which is being received by the cold body need to be supplied by the hot body. So once we calculate what amount of energy is delivered to the cold body or what amount of energy is being received by the cold body, so the amount of energy that was provided by the hot, exactly the same is received by the cold one. So based on this particular principle only, we will be we will be going ahead with all the calculations regarding this, and that is why we are specifically telling about what is the principle of calorimetry here, because entire calculations, entire derivations, entire equations what you come across this slides ahead is based on this thing only. Okay, and first of all let's have a look. Such a case is there. We are having two masses m1 and m2. Two masses m1 and m2. Of course they belong to two different material, and here you can see the specific heat is marked as C1 as well as C2. That's why I said it is two different material. Okay, now we are mixing these two material. Okay, and finally the mixture will be having a common temperature. Alright, the mixture will be having a common temperature. Now what is going to be the common temperature of that mixture? That is a concept. Okay, now you must understand one thing here. Here itself we are explaining the principle of calorimetry. What we consider here is body 1, that is specimen 1, which is at temperature T1, is having greater value of temperature. So the temperature difference, it is going to be T1 minus of temperature of the mixture. And for the second one, which was at lower temperature, so here this is the temperature difference for the first body, and the temperature difference for the second body, that is going to be T of mixture minus of T suffix 2, because it was at lower temperature. Are you getting me? Now the heat which is provided by the hot body, as per the general expression, delta Q upon M into delta T, that need to be equal to what? Specific heat. So body 1 is providing the heat. So once body 1 is providing the heat, I can have the relation as C1 into M1 into delta T of 1, that is equal to delta Q1, heat supplied by the first body. Now heat received by the second body, that need to be equal to C2 into M2 into delta T of second body, that need to be equal to what? Delta Q2. Now I told you heat received by the cold body is equal to heat supplied by the hot body, which means I can equate these two. C1 M1 into delta T1, that is C2 M2 into delta T2. Okay, now what was delta T1? Delta T1 was T1 minus of T of mixture into C1 M1, and here this is equal to C2 M2 into T of mixture minus T2. Alright, so of course now if you open the bracket and they take this term inside, here this is going to be C1 M1 into T1 minus of C1 M1 into T of mixture, that is equal to C2 M2 into T of mixture minus of C2 M2 into T2. You have got T of mix here, and here or you have got T of mix here. So this will come towards the left. So doing so, you will be getting it as C1 M1 into T1 plus C2 M2 into T2, that is now equal to what? Definitely this is going towards the right. So here this is C1 M1 plus C2M2 into T of mixture. From here I can say finally T of mixture is now equal to what? C1M1 into T1 plus C2M2 into T2 all divided by C1M1 plus C2M2. And you can see the same relation here. Okay, and here it is how we can reach up to that. Basically, this is that what you all must know. This is a standard relation, and from here you can reach up to this case. Okay, now I believe there is going to be some special cases and conditions based on that. So case number 1, what if C1 equal to C2? Definitely if C1 is equal to C2, there is going to be M1 T1 plus M2 T2 divided by M1 plus M2. What if M1 is equal to M2? It's going to be what? C1 T1 plus C2 T2 divided by C1 plus C2. And what if bodies of same mass and same material? It's going to be what? T1 plus T2 divided by 2. Same mass, same material. Okay, same mass, same material. For example, 5 kg of mass, 5 kg of water at 10 degrees Celsius and 5 kg of water at 20 degrees Celsius is mixed. Okay, so 10 plus 20 plus 10, 30 by 2, 15 degrees Celsius is going to be the temperature of the mixture. So that is how you must understand it. Alright, so delta Q1 equal to delta Q2, or you can say M1 C1 T1, M1 C1 into delta M1 C1 into T1 plus M2 C2 T2 all divided by M1 C1 plus M2 C2. That is the final relation. Okay, so from here you can reach on to any cases that you want. Now, if there is a case where ice is mixed with water and the entire ice got converted to water at 0 degrees Celsius. If that is the condition, then the temperature of the mixture, I repeat, we are having a particular mass of ice there. Fine, ice at 0 degrees Celsius is mixed with water, and in this case what happens? First of all, heat will be consumed from water by the ice to convert itself from ice at 0 degrees Celsius to water at 0 degrees Celsius. Okay, and if the heat is still left, then what will happen? This water at 0 degrees Celsius which was already converted, okay, now that water is getting mixed with some amount of water which is not at 0 degrees Celsius. Are you getting me? I can tell you what the situation is. You must understand that in this way. You are having some water. Let this be some amount of ice and let this be the water. Okay. Now for example, let this water be at 30 degrees Celsius. Okay. And capital M suffix W be the mass of water, and let this be mass of ice, M suffix I, and let this be at 0 degrees Celsius, ice at 0 degrees Celsius. Now what happens? First of all, delta Q1 amount of heat is required to convert ice at 0 degrees Celsius to convert into water at 0 degrees Celsius. Okay, so delta Q1 is going to be latent heat of fusion of ice multiplied by M suffix I. Okay, this much amount of heat will be removed from what? Water first. Okay, now you have got M suffix I mass of water. This is M suffix I mass of water at 0 degrees Celsius. Okay, now what again will be required? Now delta Q2 amount of heat will be again consumed from water, okay, to convert it to water at 0 degrees Celsius, to water at a common temperature. Water at a common temperature. So for example, say T of mixture. So in two part you must calculate. In two part you must calculate. Okay, first of all, you will be consuming some Q1 amount of heat to convert it ice at 0 degree Celsius to water at 0 degree Celsius, and from there water at 0 degree Celsius, m suffix I mass of water at 0 degree Celsius is now getting converted to water at a common temperature. So while calculating that part, delta Q2, this time you will be going for specific heat of water multiplied by mass of water that we got convert, that is mass of ice only, and we are getting converted that to a final temperature, that is T of the final mixture, because we are converting it from 0 degree Celsius to T of mix, isn't it? So delta T is going to be what? T of mixture only. So from this two part, delta Q1 and as well as delta Q2, while considering these two amount of heat, that is the total amount of heat being removed from what? That is the total amount of heat which is being removed from water, isn't it? Which was at 30 degrees Celsius. So there for water there is a temperature difference of 30 degrees Celsius to T mix. Okay, now what is the heat provided by water now? Heat provided by the water is going to be delta Q, that is supplied by the water, that is now mass of water into specific heat of water, the same thing that we used there, into the temperature difference is going to be what? Temperature difference is going to be 30 minus T of mixture. Now this particular value and this two will be substituted, because this is the total heat supplied by water and this is the two different this altogether delta Q1 as well as delta Q2, that is the amount of heat consumed by the ice. Okay, but in two different parts. For better understanding, I explain like that. Now this particular amount of heat provided should be summation of what? Delta Q1 plus delta Q2, and the game is over. And here comes the final relation for that, T of mix. So this is how we get that. I hope you got it. All right. So next topic is thermodynamics. All right. So here in this, first of course, as usual, we will be defining what is thermodynamics. Okay, and followed by that some terminologies are going to be there, and the terminologies are very important. Okay, and you must listen to that very carefully. And while coming to the work done in thermodynamic process, we will be going for a unique technology. I mean, not unique technology, I'm sorry. We will be going through a unique pattern where you can easily identify, like you can easily spot which equation you need to select to calculate the work done. And I will be connecting that work done by the system directly to the concept related to kinetic theory of gases. So that will help you to easily connect the concept altogether from KTG to thermodynamics. So that is the chain what I want you people to develop for the chapters kinetic theory, heat and heat transfer, and thermodynamics. All right. So that need to be there in mind, and always while dealing with these three topics, try to identify how they are interconnected. So if you identify that trick, this is again going to be one of the easiest topic from grade level. Okay. So as I said, first of all, what is thermodynamics? Here we are studying about the conversion of heat energy into other form of energy. Okay, we will be converting heat into another form of energy, and that particular branch which deals with the study of that. Okay, what if we got delta Q amount of heat from a given sample? Okay, now we got that particular amount of heat. Now if you want to convert that into some form of energy, directly say mechanical work done. Okay, now definitely depending upon certain conditions, this work done is going to be different. Okay, what all are that certain conditions? That conditions we will be able to identify using this terminology is leftover. So the branch that deals with conversion of heat energy to other form of energy is known as thermodynamics. Okay, now while dealing with the conversion, we can study that conversion under different situations. Okay, and here comes the first three category. First one is open system. Okay, fine. Now in this case, energy and matter both are exchanged. That means from the sample we are expecting some amount of energy. So towards that sample, from that sample, we can remove the mass, matter, as well as we can remove the amount of energy. I repeat, we are having a sample, okay, which is ready to provide some amount of energy. Okay, let it be a hot compressed gas. Fine. And from that sample, we are expecting some amount of energy so that I can do some mechanical work. Now, if I am allowed to use that gas, compressed gas, just like opening the valve or anything like that, there the gas is coming out. Okay, so that gas will be trying to expand, so I will be getting the benefit of that. And definitely once the temperature of the gas is trying to reduce, from there also I will be getting what? Additional benefit. So I was just telling, there is multiple benefits in this condition. So depending upon the situations that we have, okay, these categories are there. So first one is mass is also consumable and energy also can be removed from the given sample. That is what? Open system. Next is closed system. Okay, in this case there is possibility of what? There is possibility of energy only. That means in that the previous example that we considered, there I allowed that I opened the valve. So from that valve heat transfer took place. Okay, heat transfer took place, as well as the mass also came out. So the mass as well as energy both were consumed. In this case only energy is being consumed, the valve is still closed. That means whatever the temperature difference happening, out of that I can take the benefit, mechanical benefit. Okay, and the third one is isolated. Neither they will help us with energy, nor they are going to help us with matter exchange. So no matter is going to be exchanged and no energy is also going to be exchanged. So this is the first category. I told you the study is all about the conversion of heat energy into other form of energy, and in what way this exchange is allowed, in what way the exchange is allowed. So this was the first category, based on whether the exchange of mass, energy or both is allowed or not. That was the first category. Closed system, open system, isolated system. Open system means mass and energy you can take. Isolated system means no mass, no energy. And third one is closed system. Energy you can take, but mass I will not keep. That is a condition. Okay. Now comes the thermodynamic parameters, or which is also known as coordinates, sometimes also known as what? Variables. All right. Here you must understand what all are that variables. So these variables basically help us to identify the thermodynamic state of the system. Okay, that means these are the variables which is going to give identity to the given system. Given system in the sense, just like I will be repeating this again and again. Like for example, I am having a sample of a compressed hot gas which is ready to give me some amount of energy. Now what is the pressure of that gas? What volume of gas is there? All right, now what is the temperature of that gas? What is the density? All these are the identity of the gas. And what type of gas they are? It's monoatomic, diatomic. Okay, so these all are what? The identity of that thermodynamic system. And once a thermodynamic system, the identity of one thermodynamic system is different from that of another one, at least one among the thermodynamic parameter or coordinate, at least one will be different. Are you getting me? Now these parameters are classified into two: extensive and intensive. Okay, so these parameters, depending upon that, we can to identify this into two state, that is extensive as well as intensive as well as extensive. Okay, now what is extensive? Extensives are those which falls under the category, say you can say volume, mass, internal energy, etc. These are what? Extensive. All right. And what is intensive? Intensive variables, they are pressure, temperature, density, etc. All right. Now, thermal equilibrium. It is thermal equilibrium. What do you mean by thermal equilibrium? If two thermodynamic system is in thermal equilibrium condition, that means between that two there will not be any heat exchange taking place just because they have got identical temperature. All right. Now, adiabatic wall and diathermic wall. Now, the system from which we are expecting some amount of energy, or the system to which we want to provide energy. Okay, so what amount of energy is being consumed from the system, or what amount of energy is being provided to the system, okay, we will be calculating that based on the thermodynamic parameters. So the specimen, or that particular specimen whose pressure, temperature, volume, density, all things are being closely monitored, and based on that only we are doing some study. Okay, so our study is completely focused on that particular specimen, and it is completely based on the pressure, volume, temperature, density, etc. Thermodynamic parameters. Okay, now towards what our study is focused. Okay, that means I told you we are studying about the pressure, density, volume, temperature of some specimen. Now that specimen is known as the thermodynamic system. And what else? What else surrounding that? Okay, what else surrounding that? That we call it as what? The system. Now, what else except the system? We call it as the surrounding. And what separate the system from the surrounding? I repeat, what separate the system from the surrounding? That is, we call it as the thermodynamic wall. And thermodynamic wall is of two types, adiabatic and isothermal. Adiabatic is the one which does not allow any heat exchange between the thermodynamic system and the surrounding. That means the specimen which is ready to give us the energy, once it is covered by an adiabatic wall, you cannot expect any heat exchange from that system towards us. Okay, in other form you may consume energy, but in the form of heat transfer, energy exchange is not going to happen. And isothermal means it allows the exchange of heat, and as a result of that there is a possibility of what? The thermal equilibrium condition to take place. So adiabatic means adiabatic wall does not allow the heat transfer between the system and the surrounding. Isothermal, it allows the heat transfer between the system and the surrounding. Okay, so we discussed about what are the thermodynamic parameters. All right, adiabatic and isothermal wall. Next is work done. Okay, work done is basically, mechanically we know that it is force into displacement. Okay, now we are telling about the expansion or compression of a system. I repeat, expansion or compression of a system at any time. At any time, the force is going to be P into area, and displacement is going to be dx. Are you getting me? I repeat once again, force is pressure into area and displacement is what? Dx. Now just connect that. F into dx, that is P into A into dx, and A into dx is dV. So work done is what? P into dV or delta V. Okay, so that is how we come to the conclusion of what is the work done by a thermodynamic system. Okay, it is expanding, that is work done by the thermodynamic system. Okay, now here this is a graphical relation which shows the expansion of a thermodynamic system. Okay, that means this was the initial pressure and this was the initial volume. Now you allow the system to expand. Now after some time, this is the pressure, this is the volume. After some time, this is pressure, this is volume. After some time, this is pressure and this is volume. After some time, this is the pressure and this is volume. And after some time, this is the pressure and this is the volume. And so it's basically expanding. It's basically expanding. So once it is expanding, volume is increasing, pressure is decreasing. Now, what is the work done by this thermodynamic system now? Work done by the thermodynamic system is going to be integral of P dV, and that's going to be the area under the graph. That is very, very, very important. So here we just discussed what is work done by a thermodynamic system, and if PV graph is given, all of you listen please, if PV graph is given, then how to calculate work done by the system. So I told you here this is expansion. So if it is expansion, work is being done by the system, and if it is compression, that means work is done on the system. And work done by the thermodynamic system, in physics, work done by the thermodynamic system, we take it as positive, and work done on the thermodynamic system, we take it as negative, because our intent is the mechanical benefit. That means from the system, if I am getting some mechanical benefit, then for me I will take it as positive, and if I am losing my mechanical energy and the system is gaining that, that means for me it is negative. So work done by the system, that means the gas which was ready to expand, that is like, I would like to immediately connect that to the concept. The gas which is ready to expand, while expanding it will be giving some amount of energy to me. So that is work done by the system, and I am the beneficiary. And work is done on the system, that means me personally how to put the effort to compress the gas. So I am the loser, for me it is negative. Hope you got it right. Okay, so that is how we need to calculate the work done if PV graph is given. And of course, say I told you what is the basically, like whether it is expansion, if it is positive, if it is expansion, the work done is going to be positive, and if it is compression, it's going to be negative. Now, next is internal energy. Regarding, how, like initially while dealing with the kinetic theory of gases, we explained what is the internal energy. The total energy which is being possessed by the gas in the form of all the possible type of motion is known as the internal energy. Okay, so while telling about the gas, what amount of energy that it holds, okay, that is only going to be in the form of its internal energy, and that is by the virtue of its motion, all type of possible motion, translation motion, rotational motion, vibrational motion, all together, what are the energy being possessed by that we call it as what? The internal energy. Okay, now internal energy of the system, okay, depends on few things that we'll be discussing later on. All right, now so here you just understand what you mean by internal energy. Okay, fine. So internal energy, it has got, for a given sample, it has got direct relation to the temperature only. And if you calculate the internal energy of the system, that is, it is supposed to be what? F by 2 K suffix B into T. Here I told you in the beginning, I will be directly connecting the concept related to this one to KTG. What I told you need to be treated as F by 2 K suffix B into T. If we are discussing about gas, we can completely rely on this relation. All right. So for a given sample, of course, F is going to be what? Constant, isn't it? Now, if you keep on increasing, the internal energy will increase, and if you keep on decreasing, the internal energy will decrease. That is what you can see here. The internal energy of thermodynamic system depends on the temperature. All right, and it is the characteristic property of the state of the system. We will be discussing how that is going to change and all. All right, now next is zeroth law of thermodynamics. It's important. Zeroth law of thermodynamics says, if you have got two systems like this, okay, here this is A, here this is B, and A and B are separated by A adiabatic wall. A and B are separated by an adiabatic wall. So adiabatic wall means the one which does not allow any heat transfer between that. Now A is connected to C using an isothermal wall, and B is also connected to C using an isothermal wall. So definitely between A and C there is going to be what? A thermal equilibrium condition. And if between B and C, here also we can expect what? Isothermal equilibrium condition. So if A is in thermal equilibrium with C and if B is in thermal equilibrium with C, then though A and B were separated by an adiabatic wall, still A and B are also in thermal equilibrium condition. That is what zeroth law of thermodynamics says. Okay, and if they are in thermal equilibrium, so definitely T of A should be equal to T of C, and T of B also need to be equal to what? T of C, which means T of A is equal to T of B. In terms of temperature, if you want to say, you can go for this mathematical relation. Clear? Next is first law of thermodynamics. Here this is basically law of conservation of energy. So what it says, if you provide delta Q amount of heat, if you provide delta Q amount of heat to a thermodynamic system, then this delta Q amount of heat can be used by the thermodynamic system in two possible ways. First one is to increase the internal energy of the thermodynamic system, and the second one is to do some mechanical work. And energy what provided need to be the summation of these two, which means delta Q, that is supposed to be delta U plus delta W, and this is what we call it as what? First law of thermodynamics. Alright, and here if small amount of heat is being provided, very small amount of heat is being provided, then dQ is going to be what? du plus dW, which also can be written as dQ is equal to du plus, here this can be written as what? P into dV. And I believe you might be remembering what is this P into dV, the small work done by the gas once it was expanding to through a small volume, that is dV. Alright, so this is first law of thermodynamics, and now let us go to the classification of thermodynamic process. First one is quasi-static process, means the process, thermodynamic process. So what do you mean by thermodynamic process? Any activity that changes the thermodynamic property of a thermodynamic system. Okay, I told you about what is thermodynamic property. The one which gives identity to the thermodynamic system is known as what? Thermodynamic property. So any particular act that changes the thermodynamic property of a thermodynamic system is known as a thermodynamic process. And if this property is being changed very slowly, that means it is expanding, and you are looking at the system since last 10 minutes, even then you are unable to identify whether it is expanding or not, but it is expanding depending upon the parameters on the screen. Okay, we can see that it is expanding, but which means what? The change is happening is just very slowly. I was just telling about the variation in one parameters, that is expansion. Then such an infinitesimally slow process is known as what? Quasi-static process. Next one is isothermal process. As the name indicates, temperature change is not there. Temperature change is not happening. That is known as isothermal process. Alright. Next is, here, this is something very important. See, here I have mentioned du is equal to n times C suffix v into dt. Okay, what is this now? Here this is telling about the change in internal energy of a thermodynamic system. Okay, you might be wondering like why this your person is coming up with du term right now here. I will tell you why. Because here I told you this is an isothermal process. This is an isothermal process. Isothermal process means the temperature won't be changing. Alright. Now have a look. We all know that dq, that is equal to du plus p into dv. Isothermal process means there is no change in temperature, and once there is no change in temperature, in that condition du is going to be what? 0. And if du is going to be 0, which means dq, that is going to be what? P into dv. Which means if the thermodynamic process that happens is an isothermal process, which means the heat what you are supplying, we are dealing with conversion of heat into mechanical energy or mechanical energy into heat energy. So if I am providing some delta Q amount of heat, okay, if I am providing some delta Q amount of heat, that means that is going to be work done on the system. And if I am removing some amount of heat, delta Q amount of heat is being removed, and that is going to be equal to what? P into dV. So P into dV is work done by the system, and that will be equal to what? Delta Q. Or if I provide delta Q, that's going to be work done on the system, and that is going to be P into dV, provided there is no change in temperature. Alright. One more point I would like to tell you about here, that is that du, that is n into C suffix v times dt. Okay, what it basically represent is du is mu times C suffix v into dt. Okay, this is what particular relation says. And now I would like to throw light on to this particular relation, what it actually stands for. Basically what it says, the volume is constant. Volume is constant means here I won't allow the system to expand. Okay, I won't allow the system to expand. So it's logged here. Okay, yes. Now I am providing some amount of heat. Okay, some heat supply is taking place, delta Q amount of heat supply is taking place, and as a result of that, delta T is the change in temperature, and there itself in between at a particular instant of time, I observed dq amount of heat transfer, and as a result of that, d capital T is the change in temperature, and all this happens in constant volume. So if it is constant volume, then whatever the heat I am being supplied, as per the law of first law of thermodynamics, dq amount of heat that I transfer, it is supposed to either get converted into change in internal energy, or it need to be P dV. If this option is not there, then du need to be equal to what? dq. Okay, now see, try to connect this relation. du is equal to C suffix v into dt, and here this is number of moles of gas, because here this is molar specific heat, capital C suffix v is molar specific heat, that's why this mu term is there. So mu into C suffix v. Okay, now see, since I started discussion on this, I would like to tell you about C suffix p also. Now how to define this one is, for this I am going to have a thermodynamic system which is allowed to expand also, Okay, now once I provide dq amount of heat, and the system is allowed to expand, maintaining constant pressure. Now listen to me carefully. The temperature variation that I observe is dt. The temperature variation that I observed is what? dt. Now, in this case, as I told, the system is allowed to expand. Okay, that means the system is free to keep the pressure as constant. In that condition, if we provide dq amount of heat, if we provide dq amount of heat to the system, then we know the relation dq upon mu into dt, that is molar specific heat. And here the situation is what? At constant pressure. Then the heat what we are providing dq, that is going to be C suffix P, constant pressure is being maintained. That means that we are not allowing the system to consume the energy in the form of internal energy. That means completely it is being used to expand the system so that the pressure is maintained as constant. Okay. Now dq is now equal to C suffix P into mu into dt. Fine. Now try to understand. We had a discussion on C suffix V also. What was C suffix V? C suffix V, du is equal to C suffix V into mu times dt. Now you must keep these two relations into a single frame. dt is the temperature difference for both. dt is the temperature difference for both. Alright. So if the same temperature difference is allowed, okay, if same temperature difference is allowed, then dq, okay, if same temperature difference is happening there for a particular system, then dq, that means the amount of heat that we provided or the amount of heat that we are getting need to be calculated as specific heat at constant pressure multiplied by mu into dt. Okay, and if dt amount of course, so that is the amount of heat that we supplied. So you must understand we are having a thermodynamic system which went through a thermodynamic process, and as a result of that we are observing a change in temperature of what? dt. Okay, we are identifying a change in temperature of what? dt. Now if dt is the change in temperature, now out of that how much was the heat that we got, or we heat amount of heat that we supplied? Okay, that is dq. And what is the internal energy change? That is what? du. So temperature difference is that what we know. Now we need to identify what is dq, heat supplied or heat removed. For that we must go for the relation as this one. Okay, and to identify the internal energy change you must go for this. Okay, so you must understand you are having that a system which is undergoing through a temperature difference of dt, and out of that you are trying to calculate dq as well as du separately. That you must understand. This is the perfect relation which is going to help you. Okay, yeah, now let me go ahead. So here, so we all started with isothermal process. Okay, now we will be identifying what is the work done by a system in an isothermal expansion. So in isothermal expansion or isothermal compression, whatsoever it may, temperature remains the same. So our parameter, the measurable parameter for which we can identify the change is pressure as well as volume. If volume is measured as V1 and Vi and Vf, that is initial volume is Vi and final volume of Vf, then work done W is going to be in terms of log of 10. If you want to have an expression like this, you may have it as 2.3 approx into mu r into capital T into log, it's based to the 10 only, V of F upon V of I. Okay, or else you may have it as W equals mu r times T into ln of Vf upon Vi. In terms of pressure, if you want to represent, it's going to be mu RT into ln of, okay, into ln of what? Pi upon Pf. So Vf upon Vi, here it is Pi upon Pf. That's the condition. Alright, okay. Now, the next one is, if a situation is given where we are having bulk modulus, of a given gases. We are provided with the bulk modulus of gas, and there, of course, you know that K is going to be P value there. In that condition, you may substitute from here. You can have the value of P is equal to K and directly substitute that over there. Now, what about the PV diagram? We already discussed about this. That's an isothermal process, how the relation is going to be. Next one is adiabatic process. Okay, so in adiabatic process, basically, there is no heat exchange taking place. Okay, so once there is no heat exchange taking place, all right, so of course dq term need to be what? 0. All right, now du should be equal to what? dw. And what is du? Du is c suffix v. So du is what? Du is mu times dt into c suffix v. So here what you must understand is, for an adiabatic process, the magnitude of du is equal to dw. And do you remember what was internal energy? Internal energy is F by 2 times K suffix B into T. So I recommend you to connect the relation gamma equals to 1 plus 2 upon F. Okay, so if I have got that relation like gamma equals to 1 plus 2 upon F, okay, just have a look. What's going to be the value of F here? Here this is going to be gamma minus of 1 equals to 2 by F, or I can say F, that's equal to 2 divided by gamma minus of 1. Okay, now what was the expression for internal energy? It was F by 2 times K suffix B into T. Alright, now if I consider 1 mole of a gas, this is for 1 molecule, and if I consider 1 mole of a gas, there the internal energy for 1 mole of a gas, that is going to be, what's the value of F now? F is going to be 2 upon gamma minus of 1, okay, into 1 by 2 times K suffix B into N suffix A into capital T. So here what will happen? 2 and 2 will cancel each other. So internal energy is going to be K suffix B into N suffix A into T all divided by gamma minus 1 for 1 mole of a gas. Okay, fine, for 1 mole of a gas. And you know that this is what? Capital R. So now capital U equals R into T all divided by gamma minus for 1 mole of a gas. And for mu mole of a gas, it's going to be mu times capital R into T all divided by gamma minus 1. Okay, now just try to get into this relation. Okay, see what I derived here. This is change in internal energy. Now change in internal energy itself is going to be the work done magnitude of, isn't it? We explained it here. So in this case, the temperature is changing from T1 to T2. So of course, here capital U is now going to be mu times R into T final minus T initial all divided by gamma minus 1. This is going to be work done in what? An adiabatic process, and you can see the relation here. And for an adiabatic process, PV raised to gamma is equal to what? A constant. Okay, which means P1 V1 raised to gamma, that is equal to P2 V2 raised to gamma, and that is supposed to be a constant. Okay, so if you want to convert it in terms of PI and VI as well as PF, VF, there also you can go for it. How? Because we know that PV equals to mu RT. Okay, that means P1 V1 or PI VI equal to mu times R into TI, and P2 V2 equals to mu times R into T2. You can replace T1 as well as T2 or TF or TI from this particular relation. Okay, I recommend you to just keep this particular thing, because of course these are well connected chapters. So internal energy of a monoatomic gas or a diatomic gas or a triatomic, polyatomic, whatsoever it may, you can have the relation as what? The energy expression for energy was what? U is equal to F by 2 times K suffix B. Now F and degree of freedom as well as gamma, they are connected in this way. So that gives the connection. Alright. Perfect way to connect the equations of work done by a thermodynamic system in adiabatic process. Now, of course, the PV diagram, you must keep one thing in mind: the slope of an adiabatic process compared with the slope of adiabatic process is greater than that of an isothermal process, because there PV is equal to a constant in case of isothermal process, and in case of adiabatic process P raised to power gamma is equal to a constant. So definitely the slope is greater in case of what? In case of adiabatic process. Okay. The next one is isobaric process. Here the pressure remains constant. So once the pressure remains constant, all right. So in this case, how to calculate the work done? The work done, we know the relation dq, that's equal to du plus p into dv. Okay, in this condition the pressure remains what? Constant. So in that condition we can directly get the relation based on dw is equal to p into dv, which is equal to what? N into r into dt. And this particular relation dq is equal to n times c suffix p into dt part, and this du relation already we explained about this. Okay, and in isobaric process, as per the relation PV equals to mu RT. Okay, we know that P is constant. Okay, which means capital V is proportional to what? T. Okay, that relation is there. So based on that, you can calculate the work done. Fine. Now you must keep one thing in mind: if it is an isobaric process, so of course for isobaric expansion, this is supposed to be the graph, and here for isobaric compression, this is supposed to be the variation. So just keep in one thing in mind: we know the pressure, it's very easy to calculate the area under the graph. Okay, we need to know what? V1 as well as V2. So that's what I said. Directly you can connect it in these terms, or in terms of temperature variation. This is the relation that we have. All right. Next one is isochoric process. Definitely, as the name indicates, there is no change in volume, so work done is going to be 0. Whatever the heat provided, that's going to be in terms of what? Internal energy change only, and this is how the graph is going to be for expansion. And so here this is not what? There is no expansion or compression, because volume is not at all changing. So if the slope, if we identify, it's going to be what? Infinity. So expansion is not taking place, so work done is going to be 0 for this case. All right. Next is a cyclic process. Cyclic process means it's that thermodynamic process within which, from where the system start changing, it will be coming back to the same point. Means once the activity started, after a particular duration of time, the system will be once again getting back to its thermodynamic properties, which was exactly initial. That means the pressure, volume, temperature, density exactly is going to be the same. Okay. Now, based on that, like I am going for a case like this. That means it got expanded from A to B like this, and later on it got compressed like this because this is a PV graph. So, A to B it is expansion through C and B to A it is compression through D. So, here this is a thermodynamic expansion and here this is compression. So, we all know that area under the graph it is work done in the thermodynamic process. So, here while expanding, that is what we take it as what work done by the system. So, there the area under the graph is going to be greater. I can brief you with a bigger sketch here. This is expansion. So, this much is going to be the area. Now, if I consider the compression, so this was expansion and here this is compression, this work done on the system. So, here work done on the system is greater and work done by the system is lesser. So, if I consider it in this way, in this manner, starting from A, it came to B and came back to A. It's PV graph, okay? It's a PV graph. So, in this case, this much is the total work and the work is done by the system, okay? And if this is the condition, so here it's expanding and after that it is compressing. So, work done by the system is greater and work done on the system is lesser, and in this case the total work done is area of this much portion and here work done by the system is greater than work done on the system. That is what it is explaining here, okay? And the next one is transmission of heat. The next topic is transmission of heat. So, here we will be explaining about the three modes of transfer of heat, that is conduction, convection and radiation. Alright. So, of course, first of all conduction. While discussing about conduction, I need to tell you about the steady state first. Okay. So, if I am having, so of course, you know that what is conduction basically. Let me tell about that first. Conduction, convection and radiation. For conduction, we need a material medium, okay, and through this material medium only heat will be transferred from hot body to the cold body, okay. Here the matter content of the medium through which the heat is being transferred will not be displacing it from its mean position. Okay. Now, in case of convection, here what happens is the matter of the medium through which the heat was being transferred, actual displacement of the particle will be taking place. The cooling of room and all, it's the best example for convection. And in case of radiation, it doesn't need a medium actually. Okay. There, the heat transfer is taking place from one body to another one in the form of electromagnetic radiations. So, that is the basic difference between these three modes of transfer of heat, and I was telling about the steady state immediately after that. So, since it is connected to conduction, we need a material medium and the medium through which the heat is being transferred, okay, the medium through which the heat is being transferred, if there is no change in temperature, if there is no change in temperature for that medium happens for any particular portion of the medium, okay, then what does it mean? There is no temperature change happening. That means whatever the heat was given to the medium without even consuming even a small amount of energy out of that, exactly what was given to the medium is being transferred to the other. That means there is no leakage in between. So, what is that leakage basically? Technically speaking, that leakage means it is the amount of heat being consumed by the medium, and if that medium is consuming some amount of heat, so of course the temperature of that medium should increase. So, if the temperature of the medium is not increasing, means it is not consuming any amount of heat. Okay. So, at steady state condition, whatever the heat is being given to the medium from the hot end, at the cold end, the same amount of heat is being delivered. That is meant by steady state condition. Alright. Next is isothermal surface. Few terminologies. As the name indicates, isothermal surface. Surface having same value of temperature. Next is temperature gradient, which means if you are having a hot body here and you are having a cold body here. Here this is a hot body and here this is a cold body. Now, once you travel from hot body to cold body, somewhere at a distance of x, you observe the temperature as say theta. And after traveling through dx distance, you observe that the temperature decreased by theta minus of d theta. Now this d theta upon dx, we call this as temperature gradient. Alright. Next one is thermal conductivity. This is an area of super importance. Okay, very important area. So here what it basically says is, let me consider heat is being transferred from a hot body to a cold body. Here the temperature is T and here it is given in terms of theta. So here I would like to mark it as theta and theta minus of delta theta. That is the temperature difference. Now here this is the cross sectional area through which the heat is being transferred, and say L is the length of the conductor. Okay. Now if delta Q is the heat being transferred from hot body to the cold body within a time interval of delta T, within a time interval of delta T, T is the time taken, then this delta Q is directly proportional to, of course, the temperature difference. More the temperature difference, more will be the heat transferred, directly proportional to the area, directly proportional to the time that you allow, and inversely proportional to the length. Are you getting me? More the temperature difference, more amount of heat will be transferred. More time you allow, more amount of heat will be transferred. More area you allow, more amount of heat will be transferred. And if you are keeping it at a longer distance, definitely the amount of heat transferred in that given interval of time will be lesser. Now if I want to remove this proportionality constant, then delta Q is going to be K into the remaining terms, that is delta theta, temperature difference, area A, time allowed delta T, and inversely proportional to the length. This is exactly the same relation that you can have here. Q is equal to K into A into delta T into T upon L. Alright, now what is K? K is coefficient of thermal conductivity. Is that fine? Now please have a look. I am taking this term towards the left. Once I take this term towards the left, the general expression was delta Q, that is equal to K into delta theta into A into delta T upon L. Now I am taking this towards the left, that is delta Q upon delta small letter t equals K into delta theta into A upon L. Here this is heat transferred in unit time. Heat transferred in unit time, because delta Q amount of heat is transferred in a time interval of delta T. So here this is heat transferred in unit time, and I will call this as the heat current. We will call this as what? The heat current. This is sometimes represented as dq by dt also. Okay, and it is represented by capital H, and heat current is now equal to K into d theta, that is small temperature difference, into A upon L. Okay, now you just try to compare this with the relation I is equal to V upon R. Okay, what basically this is related to the electric current. Instead of I have got heat current here. Instead of potential difference, I have got temperature difference here. Okay, now instead of capital R, what I have? I have it as L upon K into A. Okay, so here capital R is known as thermal resistance. It is known as what? Thermal resistance. So that is what we are having in the next page. I hope I got it right. Okay, followed by the dimensions as well as the unit. It's very simple. Next is, what if we have combination of two conductors, okay, with thermal conductivity as K1, coefficient of thermal conductivity as K1 as well as K2. In that condition, please try to understand the equivalent coefficient of thermal conductivity K, that is basically this is a series connection. So in series connection, the resistance is marked as what? R is equal to R1 plus R2. Okay, and I already told you what is the relation for R. R is L divided by K into A. L divided by K into A. Just substitute that separately, you will get this relation. Alright. Now, if it is parallel combination, 1 by R is to be equal to 1 by R1 plus 1 by R2. The same thing you will get from here as well. Okay. The next one is formation of ice on a lake. That means once the temperature is low, you know that ice layer will be formed. So, if theta is the temperature difference and K is the coefficient of thermal conductivity of ice, okay, and then L is latent heat of fusion of ice and X is the difference at any time, okay, then X is the difference in the sense the thickness, thickness of the layer of the ice. Then the time taken to form that layer of thickness X, I told you this is water and this is the ice, and here this is of thickness X. Okay, then in that condition I can say the relation for the time taken, for this formation, that is going to be rho into, rho means what? Rho is the density. Okay, now rho into L is latent heat into X square divided by 2 times K into theta. I told you what is theta. Theta is the temperature difference. And if we are expecting a growth from the value of x1 to x2, a small difference, instead of x square, it's going to be x2 square minus x1 square. That is the only difference. Okay, I believe I explained all the terminologies there. Rho stands for density, L stands for latent heat of fusion of ice, okay, and X stands for the thickness and theta stands for the temperature difference between the water and the surrounding, and K is the coefficient of thermal conductivity. Alright, next one is reflectance and reflectance power of any particular body. So here ends the transfer of heat through a particular medium, that is the concept of heat transfer through the mode of conduction. And now here we are going to discuss about the transfer of heat through radiation. So once a radiation strike on a surface, okay, so the amount of energy that strike is capital E, and from here some amount of energy is going to be reflected, that is ER. Now if I go for the ratio of ER upon E for a given surface within a given time interval, this ratio is known as what? Small letter r. that is reflectance or reflecting power. Next one is absorptance and absorbing power. Again, energy absorbed upon energy which reflected for a given surface in given time interval. That is what? A. Absorptance or absorbing power. Next one is transmittance or transmitting power. The same, total energy E is supplied and ET is transferred. ET upon E is going to be T. And how they are connected. Just have a look. Total energy supplied is E. And there ER of E suffix R amount of energy is reflected, E suffix A amount of energy is absorbed, and E suffix T amount of energy is transmitted. Let me divide this entire expression with E. Here this is going to be 1, and here this is going to be R, and here this is going to be what? A, and here this is going to be what? T. So this is that relation. And if you consider a body which does not transfer any amount of heat, of course there T value is going to be 0, so then this is going to be the relation between R and A. And now consider a case where a body that completely absorbs all the amount of heat that you transmit. So definitely for that the value of A is going to be what? 1. Completely absorbed, which means R value is going to be 0 and T value is also going to be what? 0. And that happens for a perfect absorber, which is known as what? Perfect black body. Okay, perfect transmitter, T is equal to 1, perfect reflector, R is equal to 1. Alright. Next one is emissive power. Emissive power. Energy emitted per unit time per unit area of any given body is known as the emissive power. Alright. And if we want to identify what is that power for a particular wavelength, then it is known as spectral emissive power, and this is the relation connecting spectral emissive power and emissive power of a body. Next is emissivity. Okay, now that is emissive power of a body upon emissive power of black body. I repeat, emissive power of a body upon emissive power of black body is known as emissivity for a given particular temperature. Alright, and of course perfectly black body I already told you, and here they are telling about how we can practically have a perfectly black body. Okay, next one is Kirchhoff law. Kirchhoff law says that the ratio of E by A, that is emissive power upon absorptive power of a given body is always what? Constant, which means a good absorber is a good emitter also. Alright. Next is Stephen's law. Stephen's law says that the power means of course the energy emitted per unit time for a given body, that is equal to emissivity eta into sigma into A times T to power 4, where sigma is known as Stephen's constant, the value of that is 5.67 into 10 to power minus of 8. And here you must understand this is emissivity, emissive power of any body upon emissive power of black body. And if you consider the same relation for a black body, definitely the epsilon value is going to be 1. So for a black body, P is going to be what? Sigma A T raised to 4. Alright. And if we are having a temperature difference like T and T0, then for a perfect black body, this could be the relation, and for a normal one, this could be the relation, but instead of T squared, it's going to be what? T raised to 4 minus of T naught, where T naught is the temperature of the surrounding. Alright. And next is Newton's law of cooling, which simply says dt by d small letter t, the rate at which the temperature falls is going to be negative, is directly proportional to T minus of T naught, that is the difference of temperature between the source and the source and the surrounding. Alright. Now let's move to the next, that is Wien's displacement law. Wien's displacement law says that if you keep on increasing the temperature of a body, if you keep on increasing the temperature of a body, the wavelength associated to that which delivers the maximum amount of energy will keep on decreasing. And now I will tell you a very easy technique to understand. We all know that in case of electromagnetic spectrum, the visible radius, the visible radiation that comes as violet, indigo, blue, green, yellow, orange, red. So here this is the order in which the energy increases. Okay, energy increases, or you can say the frequency increases. So frequency increases in this way and the wavelength increases in the opposite way, isn't it? And initially, like you just try to understand, if we keep on increasing the heat, okay, red hot state, that is the case where the heat, like the maximum heat. See, simply take an iron rod, started heating. As initially, definitely it will get heated, but you will not be able to identify color change there. Later on, as more the heat what you provide, first of all it will turn what? Hot red. Then it will convert to almost an yellow color. And what happened in that yellow color? Just try to identify. Almost all the visible radiations coming out from that, and that is why we are getting that color which is having the mean value of lambda, that is yellow, isn't it? So first of all it got what? Red color, isn't it? So more the heat what you provide, so once the heat is increasing, the temperature of the body increased, and as a result of that, what happened? The wavelength got decreased and the energy got increased. Are you getting me or what? So the energy coming out from that, or energy being consumed by that particular body, it got increased, and as a result of that, the wavelength got decreased, and that is why it is moving the upward direction. So it's turned to red color, isn't it? So what basically says is, more the temperature increase, the wavelength associated to the radiation, the wavelength which deliver the maximum amount of energy, that will be keep on decreasing. That is Main's displacement law says, in short. All right. So the next one is oscillations. So here, first of all, we will be identifying what is periodic motion, what is oscillatory motion, and what is harmonic motion, and then we will smoothly land on to simple harmonic motion. Okay. So periodic motion means any motion that repeats after a particular interval of time. It could be any type of motion. Okay. The only thing is that repetition of that particular motion must happen after a regular interval of time. And if it is oscillatory motion, which is again a periodic motion, but there it happens in to and fro manner, okay, about a fixed position, and that fixed position is the mean position, or we can say that that is the equilibrium position. And next is harmonic oscillation. So if oscillation of any particular body can be represented by a harmonic function, then we call it as what? Harmonic oscillation. Okay. Next is simple harmonic motion. All right. So the simple harmonic motion, in case of that, again it is a harmonic motion, and in this case the amplitude of the harmonic motion, that is constant, and the force, restoring force acting on that particular body which is undergoing through oscillatory motion, that is directly proportional to the displacement, and the general expression for this one is y is equal to a sin omega t, or y is equal to a cos of omega t. Now some terminologies associated to this. First one is the time period, time taken for one complete oscillation. Frequency, number of oscillations in 1 second. Now the SI unit, it is what? Hertz or per second. Next one is angular frequency. Frequency multiplied by 2 pi, that is angular frequency. Displacement, as the name says, that the displacement of the body which is undergoing through oscillatory motion in from the mean position, that is what basically stands for what? The displacement. Next is amplitude, that is the maximum displacement from the mean position, and the next one is phase. Phase is that particular quantity. Okay, it is that particular quantity which gives us the information regarding the position and direction of motion of an oscillating particle, and normally we represent it by what? Phi. Is that clear? Here, of course, we will be having a certain mathematical relation for the displacement, velocity, acceleration, etc. for the particle which is undergoing simple harmonic motion. This particular relation we already told what this is. This is the expression for position of the particle as function of time t. And if you differentiate this, you will get the expression for velocity as function of time t. Okay, what it is going to be? If I consider this, there the expression of velocity is going to be v equals, okay, a into cos of omega t into omega. That means v is equal to a times omega into cos of omega t. This is the expression for velocity as function of time t. And if this was the expression, then it should have been v equals to minus of a times omega into sine of omega t. So here this is the expression for velocity as function of time t. And if we want the expression for velocity as function of y, then this is the relation. Okay, so here this is position as function of time t, velocity as function of time t, velocity as function of position. Alright. Next is about acceleration. If you differentiate this once again, you will get the expression for acceleration. What it is supposed to be? Here this is going to be minus of a into omega square into sine of omega t. And here, if this was a relation, then acceleration should have been minus of a omega square into cos of omega into t. Okay, now you know that a into sine omega t is what? If I go for the expression like this, if I take this as the expression for y, okay, that is y is equal to a sine of omega t. So from here, it's going to be a into sine of omega t is going to be y. That is why I am having that expression here. All right. Okay, so that is the expression for acceleration. And all this case, if this is the expression for velocity, then this is going to be the value for what? Maximum value of velocity. So maximum value of velocity is going to be same in both the case, and maximum value of acceleration, that is going to be a into omega square. So that you can see here as well. Maximum value of acceleration is a into omega square with polarity it is mentioned, that means acting in the opposite direction of displacement. That's all. Next is about the time period. So time period capital T, it's going to be 2 pi into under root of inertia factor upon spring factor. I repeat, inertia factor upon spring factor. So inertia factor is going to be mass, and spring factor we will take it as what? The force constant, that is K. So here this is the graphical variation. Considering the displacement as y is equal to a sine omega t, this is how graphically I can represent. Here this is the graphical representation for velocity, and here this is the graphical representation for what? Acceleration. Now comes the phase difference between velocity and acceleration. Between displacement and velocity there is a phase difference of pi by 2 radian. Okay, and there is between velocity and acceleration, again there is a phase difference of pi by 2, and between displacement and acceleration, between acceleration and the displacement, there is a phase difference of how much? Pi radian. Okay, now the force acting in simple harmonic motion, that means the restoring force, there in terms of x, there I took y as the displacement, and here x is the displacement. That is only difference that you must understand. So if x is the displacement, omega is the angular frequency and mass is m, okay, then I can say the restoring force F equals minus of m omega square into x. Again, I am telling you this negative sign just want to convey one information. Force is acting in the opposite direction of the displacement. That's all. Okay. And once we know this particular relation, from here I can say that omega equal to under root of k by m, and omega is 2 pi f. So from there we will get the expression for frequency or time period. I repeat, omega equal to under root of k by m, and omega is 2 pi f or 2 pi by t, capital T, where capital T is the time period. From there we can easily calculate the time period or the frequency value that we will be dealing ahead. Next is about the energy. Okay, so if x is the position at any time from the mean position, x is the position of the body at any time from the mean position, then the kinetic energy of the particle is going to be half of m omega square into a square minus of x square, and the potential energy is going to be half of m into omega square into x square. So the total energy value is going to be the summation of these two, that is going to be half of m into omega square into capital A square. That is the total energy. That is the total energy. Okay, here this is kinetic energy as function of x, nothing. It's expression for v square. I just substituted, that's all. Okay, yes, this is the expression for total energy that I already mentioned it for you, and here this is the graphical variation. Okay, now this question, questions regarding this particular graph were there many times. So here this is energy, okay, along y axis, and here this is the displacement. Okay, in all the graphs, instead of displacement marking it as capital A, by mistake it's mentioned as small letter a only, so please ignore that. Now total energy is always a constant, that you can see. Okay, how much it was? Half of m into omega square into a square. That's always a constant. And of course, when the displacement is minimum, kinetic energy is maximum. So this is the graph for kinetic energy, and this is the graph for potential energy. All right. Okay, fine. Now this is again something important. That is, of course, we know about the frequency of the oscillation of the particle, isn't it? Now the question is, what about the frequency of kinetic energy? Like how many times the kinetic energy grow from zero to maximum, or you can say decreases from maximum to minimum in one complete oscillation? It happens twice. Just because of that, you can see it is double than that of the frequency of simple harmonic motion. The same is the situation for potential energy. And if we consider it for total energy, it is not at all changing. That means the time period need to be what? Time period need to be 0. It's not at all changing. Time period is infinity and frequency is 0. Next is displacement time relation. This is exactly what we discussed in the beginning. So here we can see the same thing in a graph, a tabular column. Displacement time relation, okay, and here this is velocity time relation, acceleration time relation, kinetic energy time relation, and here on the right corner we have the expression for the maximum value as well as the minimum. The same thing here, continuing with potential energy, total energy as well as velocity. This particular part is very, very important again, because this is not in terms of time, it is in terms of x. So many a times when the displacement is half the maximum, displacement is 3 by 4 the maximum displacement value, what is the velocity? What is the velocity of the particle oscillating? In that way the questions can be asked, and how we can get down to this particular thing is law of conservation of energy, because we know that the maximum value of energy is going to be what? Half of k into a square. Okay, and that need to be half of m into v square plus half of k into x square at any time. Just rearrange this particular expression, you can get this. Law of conservation of energy, that is the easiest way to get into this. All right. Now this acceleration displacement relation, kinetic energy displacement relation, potential energy displacement relation, total energy relation, and now entire thing is focused on this. All right. Now, of course, the next is about the time period of simple pendulum. So, time period in this case, the time period is T is equal to 2 pi under root of L by G. Okay, and here let's have another case. Okay, so here this is on the surface of the earth, exactly on the surface of the earth. Now here this is a case where the length of the string to which the mass attached is very large and it is comparable with the radius of the earth. In that condition, time period was under root of, time period was 2 pi into under root of L by G. Here this time it's going to be time period T equals 2 pi into under root of, instead of L it's going to be R by R into L, okay, into L plus R all times G. Okay, next one, for a simple pendulum whose length is equal to radius of the earth, you can just substitute it over there. There the expression is going to be 2 pi into under root of R divided by 2G, and that's going to be 60 minutes. Questions were there regarding this. Now, if L is very, very large compared to that of L, of course, again, approximation in this case, there it is going to be 2 pi under root of R by G. All right. And next one is, if we are having a case where the simple pendulum is connected to a linear structure which undergo through an expansion. In that case, the time period changes to T dash equals to 2 pi under root of L into 1 plus alpha times d theta upon G, where alpha is coefficient of linear expansion and d theta is the change in temperature. Next is, what if a body is allowed to oscillate on the surface of a liquid, okay, with densities marked as rho and rho naught respectively? Then in that case, the new value of time period, okay, the new value of time period is going to be T dash is equal to 2 pi under root of rho into L upon rho minus of rho naught into G. Okay, fine. Next is, what if the system in which the simple pendulum is attached is accelerated in the forward direction with an acceleration of A. So in this case, what happens? Earlier the acceleration was G. Now the effective acceleration is going to be A dash square equal to A square plus G square, and you can see the effective acceleration is root of A square plus G square. So instead of G, it's going to be root of A square plus G square. That is the only difference. Okay. Next one is, what if the body is climbing, I mean the lift is or the setup in which this particular system is attached is climbing on a surface like this with an inclination of theta. Alright, so there it is going to be, instead of G, it's going to be what? G cos theta, because here this time G is not the acceleration which is trying to bring the body back to its mean position, it is G cos theta. So of course G is going to be replaced by G cos theta here. And what if in addition to the gravitational field, we are having an electric field also with Q as the charge of the body and capital E is the electric field, and that is opposing the gravitational pull. So here you can see the acceleration, instead of G, it is marked as G minus of Q into E upon M. So this is the new value of acceleration which is trying to bring the body back to the mean position. So again, that particular part is changed as G minus of QE by M from G. Okay. So I think you are able to identify the pattern here. Next is seconds pendulum. So the time period, any particular arrangement whose time period, that means time taken for one complete oscillation is 2 seconds, that is known as what? Seconds pendulum, and the effective length for the second pendulum is 99.992 centimeter, approximately you can say it is 100 centimeter. Next is conical pendulum, that means you are having a string and it's moving in this way. So in that condition, the time period is going to be what? T sin theta is equal to mr omega square, basically the time of one circular motion, that is what calculated over here. Alright, And next is conical pendulum. That means here you are having a rigid structure, and this is the point about which the structure is oscillating, and here this is the center of gravity. If that is marked, then the time period is marked as t is equal to 2 pi into here this is inertia factor, isn't it? So there it was mass, and here this is going to be what? Capital I, moment of inertia. Okay, capital I upon m into g into d. And now you might be wondering, what is this d? D is the perpendicular distance from the axis of rotation towards the center of gravity. Okay, next is torsion pendulum. So here we will be rotating the body like this and leaving, so it will be oscillating in this manner. So in that condition, t is going to be 2 pi under root of I by c. Again, I is moment of inertia of this body with respect to the axis of rotation, and c is restoring couple per unit twist. I repeat, restoring couple per unit twist, exactly the same as what we consider for the case of moving coil galvanometer. Okay, next is physical pendulum. Okay, physical pendulum is a rigid body oscillating about an axis, okay, but not passing through it. Fine. So there also the concept is exactly same as that of this one. So you can see the same relation here. What? T is equal to 2 pi under root of I upon m into g into d. The same relation is here. All right. And now let us move to the spring mass system. So if k is the spring constant and m is the mass attached, so here the relation remains the same. T is equal to 2 pi under root of m by k. Okay, m by k, and frequency is just going to be the inverse of that. Now comes the combination, and this is something that you must never skip. You can see two figure here. Here this is mass m, and one spring is attached like this, another is attached like this. This is parallel combination, and this one is also parallel combination. Okay, because mass is attached here. So exactly, if this is trying to pull the body in the upward direction, definitely this is also trying to pull the body in the upward direction if I pull this mass in the downward direction. Now if I do the same here, this spring is this spring will be trying to pull the body in the upward direction, and the one at the bottom, that is spring number 2, that also will be trying to push the body in the upward direction. So basically the impact on both is what? The same. Impact for both the arrangement is the same. So in that condition, for parallel combination, the effective spring constant is what? K1 plus K2. Okay, so while calculating the time period, we know that in this case, what is the time period? Time period is t is equal to 2 pi under root of m by k. So here it's going to be what? K1 plus K2. And here this is series combination. For series combination, 1 by k is going to be 1 by K1 plus 1 by K2. So again, we will be having k effective here. 2 pi under root of m by k, instead of k we are going to have k effective. Alright, next is the oscillation of a liquid in U tube. Like for example, this is the arrangement. This is the U tube. Okay, and I am having a liquid like this of height h. So I will be slightly pressing it down through a small distance. So definitely here, once I press this down, here the level will go up through a value. In this condition, the time period is going to be what? Time period is going to be t is equal to 2 pi under root of h by g. There it was L by g, here it is h by g, where h is the height. Okay, towards the main position, I can say the main position. All right. Next is oscillation of a ball in the bowl. So here, if r is the radius of curvature, then time period t is going to be 2 pi under root of r by g. Okay. Next is, what if we create a tunnel through the earth and we allow a body to fall through that one? Again, once it crosses the center of the earth, with respect to the center, it will be again oscillating, and here is the time period t is equal to 2 pi under root of r by g. Next is waves and sounds. So here, wave, you all know that what is wave? Wave is the particular form of transmission of energy from one place to another without any physical movement of the carrier or the source of energy. The carrier won't be moving from one position to another one, and second thing is that the source of energy, even that won't also be transferred from one position to, from the source towards the delivery point. That is what basically what you can say wave stands for. Okay, so here the transfer of energy as well as transfer of momentum. Both is taking place once a wave propagates from one position to another one. Now, waves are basically of three types. First one is mechanical wave, next one is electromagnetic wave, and third one is matter wave. Mechanical waves are those which need a physical medium for the transfer of energy. So, you must understand, I told here the energy is not being transferred, energy is transferred from one position to the another. Movement of medium is not taking place. Okay, the medium, the particles won't be moving from one position to another, but the medium of course it have particles, and that particle is vibrating with respect to its main position. So, please try to understand, the medium is not moving, which means the mean position of all the particle remains the same. Okay, that's what I mean to say. There is no movement of the medium taking place. Okay, so it doesn't mean that medium is a rigid, physically it is like in a something like that in a photo frame. Okay, it's not like that. The particle is vibrating, but the mean position of the particle won't be changing. Okay, now the mode of transmission of energy from one place to another, where we need a medium, is known as what? Mechanical wave. And the one which doesn't need a medium, that is known as what? Electromagnetic wave. And the third one is matter wave. That is the wave associated with a particle in motion, example de Broglie wave. All right. Now, next is nature of wave. Fine. So, here mechanical waves are of two types, transverse wave as well as longitudinal wave. So, here I told you the energy transfer takes place just because the particles are vibrating in case of what? Mechanical wave. Now, the vibration of the particle can be predicted in two ways. If this is the direction in which the energy is transferring, if the particle is vibrating like this, that means that is a transverse wave. Are you getting me? And the energy is transmitting like this, and the vibration of the particle takes place in this manner, that is known as what? Longitudinal wave. So, that is what this longitudinal waves as well as transverse wave says. Now, you must understand, in case of transverse wave, the two extreme positions of the displacement with respect to the mean position will be marked as crest and trough, and here in case it will be marked as compression as well as rarefaction. Alright. Now, what about the amplitude, wavelength and time period? Is exactly same as that of the simple harmonic motion. So, I am not going in detail associated to this one. Alright. So, here this is the velocity, exactly the same relation over there, frequency and all, fine. Now, this is the classification like infrasonic or infrasonic waves, audible wave, ultrasonic waves and all, like depending upon the decibel or depending upon the frequency, how we can classify that, the category of classification just based on the frequency. Okay. Now, here this comparison is a bit important. That means if a sound wave propagate through solid, liquid and gas. I repeat, if a sound wave propagate through solid, liquid and gas, the speed is maximum in solid and the next is in liquid and the least is in gas. That relation is important, you must know. And one more thing, of course, the sound wave cannot be polarized because it is a longitudinal wave. Okay, polarization is applicable only for transverse wave. Yeah, next is regarding the velocity of the longitudinal wave. This is very important. Very important. So, the general expression says velocity V is under root of modulus of elasticity upon density. This is the standard expression. And we will be considering this standard expression under different cases. First one, Newton said that the propagation of sound wave through gas is an isothermal process. So, as per that, we can mark it as V is equal to under root of P by rho, where P is the pressure. But Laplace said that it is not an isothermal process because the propagation of the sound is going to be that a fast process, the system won't be getting the time to exchange the heat and to maintain the temperature. So he said it as an adiabatic process. So just because of that, we will be marking it as under root of gamma p by rho. Because here the modulus of elasticity is what? Gamma times p. Next is factors affecting the velocity of longitudinal waves. First one is the effect of pressure. We just derived the expression V is equal to under root of gamma p by rho. Here this is not R, it is gamma p by rho. Alright. Now from the relation PV equal to mu RT, we can convert the same as V equals under root of RT by M, which means if the temperature is kept constant and if you change the pressure, the speed is not going to change. Okay. Next, effect of temperature that we already discussed here. V is proportional to root of T. So V1 by V2 is going to be root of T1 by T2. Alright. Next is effect of density. Earlier also we discussed this. V1 by V2 is going to be under root of rho 2 by rho 1 because V is proportional to 1 by rho. Next is effect of humidity. If more the humidity, then lesser will be the density, and if density is decreased, of course speed will be increased. I repeat, more the density, more the humidity, lesser will be the density, lesser the density, greater will be the speed. Next is characteristics of musical sound. So you must know what is basically loudness, what is pitch or frequency, and what is the quality or timbre quality. The loudness, that basically is the intensity. Pitch, that is connected to the frequency. Quality, that means how comfortably we are perceiving a particular sound. Okay, that means basically the musical notes, like if a musician is playing piano for you and if I do the same, the difference in that gives the quality. Okay. Now next is the speed of transverse motion. Of course here till now we were telling about the longitudinal waves. Now this time it is transverse wave. Okay, and it is allowed to propagate through a string which is stretched with a tension T and M is the mass and let L be the length. Now speed is capital T all divided by small letter m. Here this is mass per unit length. What it is? Mass per unit length. It is not mass, it's mass per unit length. Okay. And next is equation of propagation. I recommend equation y is equal to a sine of omega t minus of k into x. From here you can get into any format that you want. Just replace k divided by 2 pi by lambda and omega is 2 pi f. So this standard expression will take you to any of the format that you want here. Alright. Next is the coefficient of propagation. Coefficient of propagation is what? Here I wrote this as k, na? Isn't it? Fine. So this particular relation, how it came, that you must understand. Any disturbance that happens at the origin, if it is a simple harmonic motion, it can be marked as y is equal to a sine of omega times t. And if I am having a point which is at a distance of x from the origin, that means the source. Now here whatever the disturbance I am receiving, that will be exactly the disturbance which was taking place at the origin at a time of t is equal to x by v times behind. So how I can explain this particular disturbance as y is equal to a sine of omega into t minus of, here this is going to be what? X upon v. So this is what that basic relation, y is equal to a sine of, okay, this will go in, that is omega t minus of omega into x by v. Now omega is constant, v is constant. Now omega by v, that is what? k. All right, fine. So this is that particular relation, okay, omega by v is equal to k, and k is also known as what? Propagation constant. Now here the wavelength, angular frequency, time period, particle velocity and all. Okay, particle velocity you must understand, it is dy by dt. Okay, it's not this v here. We had an expression here, this as v, na? This one. This is the speed by which the wave is traveling in the forward direction. And with what speed this particle is vibrating, that is particle velocity, that is dy by dt, rate at which the position of the particle is changing with respect to the main position. Okay, so here this is wavelength. Okay, I told you how wavelength is connected, that is directly connected with what? That k term over here. What was that k term? Because omega, what is omega? Omega is equal to 2 pi by t. Okay, and v is equal to what? Lambda is equal to v into t. Okay, just by substituting that you will get this relation. All right. Next is about the phase. So here what is phase? Phase is 2 pi into small letter t upon capital T minus of x divided by lambda. Again it came from this particular relation only, this entire thing. Altogether we call this as what? The phase as phi. Okay, and now it is again the same thing only. Fine. Yes. Now next is the energy of the propagating wave. Okay. Now here regarding this, I want to introduce three terms. First one is energy density U. Next one is power and intensity. Energy density, power and intensity. Okay. Have a look. First of all, kinetic energy per unit volume of a propagating wave, that is half of rho into omega square into a square into cos square kx minus of omega. Basically, we took the expression for v. We took the expression for v here because dy by dt, that will be giving the expression for v, and I just used that. And here this is the expression for the displacement, half of kx square, that is converted into the form of displacement at any instant of time, the standard expressions. Now here comes the total expression. Okay, I mean the total expression for the total energy, and here this is the expression for energy density, and this is the most important thing here, energy density. Okay, and here this is the expression for energy density, and here this is expression for total energy per unit volume, and here this is potential energy per unit volume, and here this is kinetic energy per unit volume, and you can see the relation here. Kinetic energy per unit volume, potential energy per unit volume, the expression is exactly the same thing. Adding together you are getting this one. So the total energy can be exchanged, isn't it? Fine. So yeah, so that exchange is taking place, so the average value remains the same for both, and here this is energy per unit volume, that is energy density. Okay, and you must not miss something important over here. The energy density, small letter u, it's directly proportional to square of the amplitude. Now comes the power. Power is energy density multiplied by volume, that is energy delivered per unit time, that is what we call it as what? Power. All right, so you can see that particular term is appearing here, where that half of rho into v square times a square, that stands for energy density only. Now comes the intensity. Okay, intensity is energy delivered per unit time per unit area. Now here surface area will be need to be considered. So here in this case, in case of intensity, we had this s multiplied by v term, where v is the propagating speed. So here this is going to be the volume which is covered by that particular wave in unit time, isn't it? So that is that s into v we considered. Now while considering the intensity part, so energy delivered per unit time per unit area. Okay, so definitely we need to divide it with s term there. So once you consider it here, you can see in this case this was the power, isn't it? Half of rho into omega square into a square into s into v is there. So in this case, s is not there. So here this is the expression for intensity. So here in case of intensity also you can see that it is directly proportional to square of the amplitude. Okay. So you must be able to connect the relation. Small letter u, it is half of rho into omega square into a square. Power p, that is half of rho omega square a square s into v, and intensity I, that is half of rho omega square into a square to v. Alright, yes. Next is superposition of wave. You know that when one wave is superimposed over the another one, that means simultaneously two or more than two waves are passing through a single point. So it will individually contribute to the effective displacement and the total displacement experienced by the particle through which that two or more than two waves are simultaneously passing. It is going to be the vector sum of the individual displacement caused. Okay, that is not we call it as interference. Next is constructive interference. So what do you mean by constructive interference? If two waves simultaneously reach at one particular point and the amplitude is increasing, that means individually wave was reaching there and it was creating a displacement maximum up to small letter a. Now second one is able to create a maximum displacement of b. Now altogether if the effective displacement is increasing, basically that is known as constructive, and if it is decreasing, that is known as what? Destructive interference. So for constructive interference we need the phi value. That means here we had an expression for cos of phi, no? So in this case we need this to be what? Plus 1 for constructive, and for destructive we need to be what? Minus 1. So based on that, if it is minus 1, then it is going to be what? A of a. If of course if this is going as minus 1, so then it's going to be a square plus b square minus of 2ab, and if it is plus 1, of course root of, and if it is constructive it's going to be what? A square plus b square plus 2ab. So this is going to be constructive and this is going to be what? Destructive. Okay. Now, so this is the case of maximum and minimum. Fine. Now comes the beats. Alright. Now while coming to the beat frequency, so what basically stands in this case is, let us consider two sound wave, okay, comparatively lesser difference in the frequency value simultaneously reaching at a particular point. So there what happens is, once these waves are simultaneously reaching at a particular instant, the sound will be maximum, again it will be decreased, again it will be increased, and again it will be decreased. So within a time gap you can identify the sound is increasing, decreasing, increasing, decreasing, increasing, decreasing. This is what we call it as what? Beat. And the time interval, the time gap in which this happens, increasing and decreasing happen, that is known as what? Beat frequency. And what basically the beat frequency is, that is the difference in the frequency. Alright, and you must understand one thing, here in this case, if this particular phenomenon need to be observed, then the difference in frequency should not be more than 10 hertz. Okay, that is very, very, very important. And here, and I told you the intensity will be greater. So here the maximum amplitude is going to be what? A1 plus A2. Okay, and the intensity is going to be what? The square of that thing. Okay. Next is reflection of wave. If a wave is moving in the forward direction, I mean in along positive x-axis, this is going to be the equation of propagation. And if it is one is traveling in the negative direction, this is going to be the equation of propagation. So here this negative sign, like between kx and omega, opposite sign is there. That means if this is traveling in the positive direction, and if they bear the same sound, which means this is traveling in the negative direction. Alright. Now echo as the name indicates, sound will be traveling from one source to a surface, from the rigid surface that will be reflected back, and we hear the same sound after a particular time gap, that we call it as what? Echo. Alright. Now, next is stationary or standing waves. So, once we consider a wave which travels in the positive direction, and once it reaches there, it will be coming back. Now, we are having a wave which is traveling in the forward direction. We can call it as y is equal to sine of omega t minus of kx, and from there it is reflected back. So, always remember, once it is reflected back, okay, now let us consider a case of transverse wave. There, of course, amplitude will be reversed and the direction also will be reversed. So, this will be getting superimposed, and the resultant of that can be represented as y is equal to 2k into cos of omega t into sine of kx. Alright. Now, you must understand one thing. Here, with respect to time, the amplitude is changing, and with respect to x also the amplitude is changing. Isn't it? Cos of omega t with respect to small letter t it is changing, and sine of kx with respect to position also changing, which means if this is what you see at a particular instant of time, after t time you can see it's decreasing like this. After t time again it will be decreasing like this. After t time it will be a straight line. So, this is how with respect to time it is changing, and after that it will be again growing in the same fashion. So, that is the variation in amplitude with respect to time, and here this particular portion it is at state of rest all the time. This is what it represents, what? The change with respect to x axis. And one more thing, now you must understand this is the extreme, okay, displacement. Now, for that also you can see here there is x equal to 0, displacement is 0, and x equal to say this particular distance, there the displacement is maximum. Now, you just try to understand, this altogether gives a complete wave. That means this is lambda. At a distance of lambda by 2, displacement is 0, and at a distance of lambda by 4, displacement is maximum. That is what I said. Here the displacement is varying with respect to time, and the displacement is varying with respect to x also. Are you getting me? So, that is why I can say this is the mathematical relation for what? The standing wave. Okay. And of course, I told you about this displacement over here. So, the position from the origin where no displacement take place, I repeat, no displacement, they are called as what? The node. And node is at a distance of, what you observed here, it's at a distance of lambda by 2. Okay, here this is at a distance of lambda by 2, here it is at a distance of what? Lambda. Now, you can see that particular relation here. Okay, fine, clear? This is at a distance of what? Lambda by 2 from the origin. Okay, and here this particular distance, I told you this is lambda by 4, and we call this as what? Antinode. Okay, and please remember one thing, the distance of separation between two successive node or two successive antinodes, again it is going to be lambda by 2 only. So, that is also a point that you must understand, and here this is the general expression. Okay, here this is the general expression for two successive nodes or antinodes, that is all. Alright. The next one is the position of nodes. Like this we already explained what is node and antinode. The position of this one is just based on that sine of kx. I told you, no, here this is having two parts, sine of kx and sine of omega t. So, just by putting that is equal to 0, you are getting this particular relation. Next is position of antinodes. We already told about this, where the position is going to be for node and where it is going to be for antinode. Basically, you just need to take care of this. Where it is 0, that is going to be node, and where it is 1, that is going to be antinode. That means sine of kx is equal to 0 means node, and sine of kx is equal to 1, that is going to be antinode. That is all. It is as simple as that. Next is vibration of the stretched string. Okay, this is something very important. Alright, now please have a look. The frequency of the string, how it is connected to the length. Frequency is proportional to 1 by L, point number 1. Frequency is proportional to root of tension. Frequency is proportional to the linear mass density as V proportional to 1 by root of mu. Okay, and how it depends on the radius of the string, N proportional to 1 by R, and how it depends on the density, frequency N proportional to 1 by rho. Very, very, very important. Inversely proportional to L, directly proportional to square of T, inversely proportional to root of mu, inversely proportional to root of rho, and inversely proportional to R. Okay. Next is vibration of a string fixed at one end. For this, let this be the string and this is that end which is fixed. Now, if we create a wave form with fundamental frequency, this is going to be the shape of the wave. And if I mark this as the length, the length L, that is going to be V, that is going to be what? Lambda by 4, because you know that this is that complete wave and we are having this much portion only, that is lambda by 4. And we all know that lambda, that's equal to V into T, which is V upon F. Alright, so once I substitute that value here, this expression is now going to be L equals, instead of lambda, I am going to have it as what? V upon F into 4. Now from here I can say that frequency F is going to be what? V divided by 4 times L. Alright, now what is going to be the next? If I consider the next, then this was the fundamental frequency, this was the length 4, the fundamental frequency, and now this is going to be the length. That means, see, I can mark it like this. Okay, so just have a look. Now this is going to be the length of the string. There it is, lambda by 4, 2 lambda by 4, 3 lambda by 4. That means 3 lambda by 4, that's going to be L. Now you will be replacing this lambda by what? V upon F. Here this is 4 and here this is 3 and here this is what? L. In this case, frequency F, that's going to be what? 3 V divided by 4L. I hope you got the technique. 3V by 4L. Next is going to be 5V by 4L. Next is going to be 7V by 4L. So this is how you get the fundamental frequency if the string is fixed fundamental frequency, and the next one is what? The first harmonic, sorry, third harmonic, next one is fifth harmonic, so and so and so. Alright. So how we identify this, like how we can say that is first harmonic, third harmonic, and see, this was the fundamental frequency, isn't it? Now here comes the next and here this is the third one. Okay, that is why we call it as what? Third harmonic. Okay, because how many such parts are there? Here this is the first part, here this is the second part, and here this is the third part. It will keep on going like that. Alright, next one is standing wave in case if both the ends are fixed. In this case, we had it as what? One end fixed. Here it is both end fixed. So here this is the length L, and here this time it's going to be what? Lambda by 2. Now here this is the length, here it is going to be 2 times lambda by 2 or lambda. Here L is the length, here this is going to be 3 times lambda by 2. I hope you got it right. Okay, that is how we identify the fundamental frequency. And next one is open pipes. So in case of open pipe, this is the fundamental waveform, both ends open. Now just try to understand this entire length, this is lambda by 2. So the length of the pipe is going to be lambda by 2. Now here this is what? Lambda by 2. Here this is 3 lambda by 2. okay, because this is what, lambda by 2 here, am I right or what? This particular portion, just try to understand like this. This is lambda by 4, sorry, this is lambda by 4, here this is lambda by 4, here this is lambda by 4, and here this is lambda by 4. So this entire portion is going to be lambda by 2. Okay, that entire portion is going to be lambda by 2, and here this is what, lambda by 4. Okay, and here this is lambda by 4, and here this is what, lambda. Here this is lambda by 2, lambda by 4, lambda by 4. All right. Now have a look. Here this is lambda by 4. Here this is lambda by 2, lambda by 2, and lambda by 4. Okay. So how you must understand it over here is, this particular part is lambda by 4, and here this is lambda by 4. So this is 2 lambda by 4. Now 1, 2, 3, 4, 4 lambda by 4. 1, 2, 3, 4, 5, 6, 6 lambda by 4 equal to L. In this way you can substitute. Okay, so the standard expression is L is equal to, okay, the length is going to be the standard waveform, isn't it, in terms of lambda. In terms of lambda, here how much it is? I told you this is lambda by 4, and here this is lambda by 4, isn't it? That is 2 times lambda by 4. Okay, this is the expression that you must put, and you need to put lambda as what? V by F. That's all. Clear? The next one is variation in closed organ pipe. That means in this condition we are not going to have, you know, both end open, we will be having one end open. So here this is the fundamental way. Okay, so here this is lambda by 4 equal to L. Now the next one is 1, 2, 3, 3 lambda by 4 equal to L this time. Next is 1, 2, 3, 4, 5, 5 lambda by 4. Okay, fine. This is how we identify the fundamental frequencies and harmonic frequencies. Alright. Next one is end correction. Alright. So the end correction, the only part is while considering the effective length. While considering the effective length, we will be exactly the waves coming over here, it will not be onto the tip. There will be some correction, and that correction is marked as what? End correction, which is represented by small letter e. Okay, what I mean to say is that the node or anti-node, okay, in this case of pipe, it's supposed to be what? Anti-nodes. So this anti-nodes exactly won't be appearing onto the exact tip, it will be having a small difference. So if that small difference is considered, we consider it as what? Small letter e. And if we have an open organ pipe and a closed organ pipe, so for open organ pipe, 2 ends are open. So correction at both the ends need to be considered. That's why we are taking it as what? L plus 2E. And if it is a closed organ pipe, it's going to be what? L plus E only. Alright. And the next one is factors affecting the frequency of the wave in the pipe. Again, as what we discussed, the same thing in case of the string. Here also the length of the column proportional to 1 by L, radius of the air column proportional to 1 by R, temperature proportional to T, pressure difference proportional to root of P, density proportional to 1 by root of rho, and velocity proportional to V. Okay, so the temperature exactly you can see it as in the case of what? Earlier also we discussed, na? Fine. So it's the same part, it's appearing here as well, and how it is varying with respect to density, the same part you can see here as well. The next one is resonance tube. Resonance tube is nothing, it's exactly the same as that of the case that we considered in case of that closed end organ pipe. You will be having the same calculation exactly same as that of the closed end pipe. Alright. So that was all from my end for this all chapters. We will be meeting soon with the detailed discussion for your last part test. Till then, bye bye and take care.